हेलो, चेक। This is Vikram Gota here. So there is a slight change in the program today in terms of the speakers who will be kind of delivering the talks, not the agenda itself. The agenda will remain the same, but the first two talks, which is statistics for beginners and advanced statistics, will be taken by Dr. Mahesh Iyer, followed by Dr. Sadhana Kannan, who will discuss the survival analysis. Okay, so please note this minor change in program. And to introduce Dr. Mahesh Iyer, I have known Dr. Iyer for the last 5 years, and he has been with us ever since we started AAZPIRE in 2021. He is a statistician par excellence. He has worked in several pharma companies in the past, including Novartis, BMS, and so on. And now he is a chief biostatistician at Pfizer, and he has a passion for teaching so not surprisingly he was involved with us right from day one. And in fact, not only here, but he also is a consulting statistician for us because we run a postgraduate diploma in biostatistics, and then he also helps us in our teaching program for our students. So and he is a fantastic teacher. I've heard him last 3 years, and then I'm sure he will keep it very entertaining, at the same time very interesting, so that the concept that you learn here today will not be forgotten forever. So with that very small introduction, I would like to invite Dr. Mahesh Iyer to come and give his talk. Thank you.
Thank you. So guys, so we have a fair bit of material to cover today, and unfortunately not enough time. Okay, so I'm going to go a little fast. I'm going to skip over a bunch of slides. We made this change happen in terms of the topics. So I'm going to pull from 3 or 4 different presentations that I have so that we can focus on the relevant material. Yeah, so I'll keep changing that. Normally, for folks who have attended some of my sessions before, normally I like to work with a whiteboard and different colored pens. Obviously, we can't do that here because 1, we don't have a whiteboard, and 2, we are also online. So I'll try and do that on Microsoft Paint, because there's just one aspect I think which is tremendously important, which is better if I walk you through as we are developing it. So I'll try and do it with Paint. So it won't look very good, it'll all be squiggly, but at least you'll get the concept right. Yeah, so we'll go with that. Okay. My only request to you is we just have about an hour. So for 1 hour, I know all of you have a lot of protocols to write, things to finish. Yeah. Extremely important WhatsApp messages to check, understand what's going on with politics in the country, right? But for 1 hour, can I ask you to put away all your devices? Okay, because what we're going to talk about is, I'm not going to turn you into a statistician, right? That's not the point, because I need my job, right? All we're going to try and do is explain some very, very basic concepts so that when you read, when somebody tells you something about what is needed in stats, there is at least a sense that you will say, this is probably what they mean. Okay. Good enough? So we have a deal? No laptop, no phones, no nothing for 1 hour at least. After that, Sadhana can do what she wants. No? If she's okay with you guys checking, that's okay. That's on her. Okay. ये कनेक्ट करना है ये नहीं क्या है वो दूसरा वाला Perfect. All right, good. So we're going to start with something really, really basic, okay? Because a lot of people keep talking about population, sample, population mean, sample mean, all of those kinds of things, okay? So we're going to start with something very, very, very basic, all right? Let's start with, sure. ये है क्या? Column mic या hand mic है क्या? हाँ. I feel very constrained if I'm just standing there. Okay, so let's start with something as simple as data, okay? How many different types of data are there? Mainly? 1? 2? Okay, so let's say broadly 2 types of data. What are the 2 types of data? Quantitative and qualitative, right? Numbers, text. Simple, right? So quantitative is numbers. Agreed? Okay, mostly we deal with numbers. When do we deal with text? What is an example of text data in the clinical research setting? Surveys, but surveys could also be numbers, no? So for example, you could say, tell me what your pain score is on a scale of 0 to 10. That's still a number, no? What is an example? Quality of life could also be a number, right? Correct? You can have SF36. All the things in SF36 is a number, right? Yes or no is again 1 or 0, could be a number. Yeah? What is an example? Come on, stage of tumor. Not necessarily a number, right? Severity of adverse event. Not a number, right? Mild, moderate, severe. Correct? Location, primary location of tumor. Yeah? Not a number, correct? So those are the qualitative data. Okay? And if we want to work with qualitative data, how do we do? What do we do normally? Qualitative data. Wow, chi-square, too much. You can use chi-square, it's a very good thing. But what do you normally do with qualitative data? If you have to show qualitative data, how would you do it? To describe it? Yeah, what kind of descriptive statistics would you use for qualitative data? Bar chart is a graph, correct? What does a bar chart signify? What are the height of the bar chart? Frequencies, correct? So you would say I have 10 people with stage 2, 3 people with stage 3 and so on, correct? Or I would say I have 7 with liver, 8 with gastric, 9 with prostate and so on, correct? So you basically would use frequencies to describe qualitative data, correct? What would you use to describe quantitative data? Very good. I heard somebody say means. Yes. So mean is 1. Median is 2nd. Mode is 3rd. When do you use mode? You never use mode. Only Gulzar uses mode. किस mode पे आते हैं? That mode. No? When do you use mode? No. Outliers, yes, but outliers you typically use what? Median, right? If you have, let's say if you want salaries of all of us, okay, your stipend, okay, let's say average of 100 rupees. Yeah, suddenly you add Dr. Vikram's salary, average 500 rupees. Yeah? Why? Because only his salary will pull all your salaries away, right? So when you have 1 or 2 outliers like that, you use median, correct? But when do you use a mode? Actually, you don't use a mode much in clinical research, truly. Yeah, you can use a mode to say, a mode is what? The highest frequency, correct? So if you want to say what is the highest frequency of, let's say, what type of tumor, right? Where or primary site of tumor, you can use a mode for those kinds of things, correct? But a mode really, if you want to really think about where you use a mode, you actually use a mode a lot in retail settings. Yeah, if you were to go to Shoppers Stop, yeah, what shirt size do you think they would keep? The mode, right? They're not going to do median. They're not going to mean. Actually, most people are either 42 or 44. I'll do a mean, so 42.3. There's no 42.3 size, no? So there, when you stock things and retail and other kinds of things is where you use a lot of mode, okay? But other places, mostly in our clinical research, we either use a mean or the median. Have you guys ever used median, ever? Have you seen any paper where they talk about median? Yes? In what setting? Overall survival. Very good. Excellent, right? So you talk about median overall survival. And why do you talk about median there? Versus mean? I'm sorry? Yeah, that's correct. 50%. Median is 50% of the patient. But why are you using median versus mean there? Not just one outlier, a few outliers, no? Because if you think about survival, let's say you take survival with breast. Breast is very long anyway, most of the time, right? Let's say you take survival with something very bad, pancreatic or something, yeah? What will happen is that you tend to have a lot of people having low survival, right? 9 months, 11 months, 12 months, 2 years, things like that, right? And then you'll have 1 or 2 people with 5 years, 7 years, correct? So it's 1 or 2 outliers pull everything away. Correct. So there you want to use something like median. Okay. But Sadhana will come and talk a little bit more about survival per se. Okay. I am going to talk primarily about the mean. And you know why? You know why I'm going to talk primarily about the mean? Hmm? The reason is because we are going to deal with samples and not with the population. Okay. So do you understand the difference between a population and a sample? What is the difference? What is the population? Perfect, right? So population of Mumbai, sample at this hospital, at this particular venue. Excellent, right? Is this a good sample? Not really, no? Because all the people here are interested in listening to clinical research, which is a fraction of the Mumbai population, right? So it's not really a representative sample. It's not a great sample, but it's a sample nevertheless. So a population, if you think about it in clinical research terms, is if you take prostate cancer stage 3, yeah, a population is all the people in the world who have prostate cancer stage 3. Okay. What do? You draw a sample from that. So if you look at that slide, the total population is all patients with lung cancer. Okay. Do you know what that size is? No, right? Because you really don't know. You can only estimate it, right? So you don't know what the size of that population is. What you now do is you draw a sample. Let's say you draw sample 1 of 100 patients. Okay. And you keep on doing that. So this study is done at TMC Kolkata. Okay. N1 patients. And then you do another sample of N2 patients, which is done at ACTREC. Okay. You do a third sample with N3 patients and so on, which is done at ADR and so on. Okay. So you keep on drawing samples from this population. Make sense? Yeah. So everybody understands population and sample. Okay. So next what happens is you have an overall sample population mean. Okay. This is what you're trying to find out, or a median. Let's say whatever. Okay. You have an overall. What you're trying to do is you don't know what that overall is. Yeah. You don't know what that overall mean or median is. You don't know what the median survival of all lung cancer patients in the world is. Yeah. But what you do know is once you take a sample, let's say of 43 patients, you know what the mean or median of that sample is. Make sense? Okay. So TMC will have one sample 24.7, TMH will have another sample, let's say 24.8, ADR might have 24.2 and so on. So different places, when they take these samples, they get different values of mean and median. That's why there is a difference. That's why the samples are different from the population. Okay. So what is a sample mean called? There is a term we use for it. You know what it is called? Okay, what is a sample mean called? How do you denote it? When you read papers or other kinds of things, you see the sample mean denoted, right? How is it denoted? Sorry? Z. Z is a test. We'll get to testing soon. But what is the sample mean called? It's called X bar. Right? Why is it called X bar? Because you're saying that each value here in the sample is some quantity X1 that you can observe. So you have X1, X2, X3 and so on up to X43. Yeah? You take a mean of all of that, you get X bar for sample 1. Yeah, but you get X bar for sample 1, you get X bar for sample 2, which is different, you get X bar for sample K, right? Sample 3 and so on. So you get all these different X bars. Exactly. So what do you say about it? You say that the mean of sample 1 is 24.7. Mean survival, mean whatever, mean let's say mean proportion of whatever, okay, mean size of the tumor, whatever that may be. Okay. So let's say it's not mean, it's median. You can say median survival is 24.7. Make sense? Of sample 1, of your sample. Okay. So, but the population mean is called mu. Okay. Now, one thing that you have to remember always is anything that is relating to the population that you don't know about is a Greek letter, mu. Okay. the population proportion. What is the proportion of responders in the population? You don't know what that is. You know what it's called? Pi. Okay? Anything to do with a sample that you can observe and know is English. Sample mean X bar. Sample proportion P. Population proportion is pi, sample proportion is P. So the corresponding English letter is the sample. The Greek letter is the population. Easy? So anytime you see a Greek letter, it means it is something to do with the population is unknown. I don't know what it is. I can only estimate it. Makes sense? Yeah. So this is what we do. Okay, so you have a sample, you have a population, you have a sample. Okay. And now obviously the population, there are people that have different values, right? If you take mean or median survival in the population. Okay, some people may live for 6 months, some may live for 12, some may live for 24, correct? Some may live for 30, 35, 40, 80, 120, right? So there are different values. What is that value of difference called? Very good. Variance or standard deviation. What is the population variance denoted by? Sigma. Okay. Now you move to the sample. Now in these 43 patients also there is a variability. Okay. But once I take the mean or the median, okay, now there is still variability between the different samples, correct? Yeah. So what is the sample, the variability within the sample called? Again, standard deviation. What is it denoted by? No, population of sigma. So what is this denoted by? What is the English? S. So the English equivalent of sigma is S. So it's denoted as S. Make sense? So S is your sample standard deviation. Sigma is your population standard deviation. Okay? Now there is another concept which is that between these samples there is variation. Correct? So this is 24.7, this is 24.8, this is 24.2. Correct? Will this variance between the samples be more than the variance within a sample, within the population, or less? Think about it. You're already taking a mean, you're already taking central values. So it'll be much lesser, right? Yeah? And what is that quantity called? It is called standard error of the mean. Okay? It is called standard error of the mean. Error of the mean is between the samples. Yes? Makes clear? Everybody understands? So that is what you have to think about. The standard error of the mean is always going to be smaller than the standard deviation. Okay? By what order? Think about it. If your sample sizes were very, very large, 1,000 patients, 2,000 patients, then the means are likely to be more accurate, right? More closer together. Whereas if your samples are very small, 2 patients, 5 patients, 10 patients, then there is still a lot of variability between the means, correct? So the standard error of the mean is a function of the sample size n. Yeah? And what is the exact formula? It is actually the sample standard deviation S divided by square root of n. Yeah? So n is always greater than 1. You can't have a sample of size 0. Correct? So the standard error of the mean is always smaller than the standard deviation. Make sense? Yes? Okay, so now what have you found out? You have found out that these samples themselves have some variability, which I'm going to call standard error of the mean. Okay. I can also take the average of these samples. Yeah? Okay, so the true mean is 24.2. But you see, and somehow you know that, okay? You don't know how, but I'm God, because most statisticians are gods, okay? So the true mean is 24.2. Yeah? And around 24.2, you get all of these different values. Make sense? Yeah. So now what you have is a picture like this. Correct? So true mean, let us say, is 23.9. Yeah? You typically don't know this. But then you have all of these different samples with a mean and the standard deviation around them. Make sense? Okay. So these things, the red dots themselves, is called the sampling distribution. Okay. And one of the most magical things, and if I had time, I would go through exactly how that works. But one of the most magical things is that these means, yeah, will always follow a normal distribution. You guys know about normal distribution? Gaussian distribution, bell-shaped, yes. Mode, yes. They always follow the normal distribution. Okay. It's a property that is called a central limit theorem. It's a theorem. Okay. What is the difference? What is the point of a theorem? A theorem means it is always true. Yeah. It's a theorem that essentially says central limit theorem. So the means, not the populations themselves, okay? The means, not the samples themselves, but the mean of the samples as your n becomes large. If your n is very small, 10 or something, then it won't work. But if your n is large, and what is large? What is a good number for large? Large is a very greater than 30. I don't know why, but everybody likes 30, so we'll take 30. Okay. Yeah, I don't know why 30, but everybody likes 30, so we'll do 30. Okay. So if your n is typically greater than 30, your sample size is typically greater than 30, okay, then these tend to follow a normal distribution. What is the mean of the normal? The normal distribution has two things, right? Two parameters, right? What does it have? The mean and the variability, correct? What is the mean? The mean for this, sampling distribution, what would the mean be? The beauty is the mean is actually equal to the population mean, mu, which you don't know. Okay, but these would always be centered around the mean. So irrespective, when you take a sample, you expect that it will be close to the population mean. Okay, and with a standard deviation of, what did I say before? I said, what is the standard error of the mean? S divided by square root of n. Okay, get it? Okay, so what is the beauty of the normal distribution? What is one of the beauties, like, what is the characteristic of the normal distribution? If you take the mean and do plus or minus 1 standard deviation, what proportion of data do you expect to be there? 65%, right? 66%, correct? If you take plus or minus 2 standard deviations, then what 95%? Yeah. So the beauty now is that if you take any sample, reasonably large sample, let's say you've done it right, you've done it homogeneous, you've not cheated, you have not put only one kind of patients in, okay, you've done as best as you can. Let's say you take that, you take your mean of that sample x bar, you take 2 standard deviations, standard error of the mean, s over square root of n. Okay, you take 2 of those on either side. That confidence interval is called a 95% confidence interval for the true population mean, which means that you are 95% sure that this confidence interval will actually contain the true mean. Okay, so for example, if your confidence interval is, let's say, 6 to 10, your mean is 8. Okay, standard error of the mean is 1. Okay, so plus or minus 2. 8 plus or minus 2, 6. 8 plus 2, 10. If you take this 6 to 10, what it means is that this 6 to 10 will contain the true mean 95% of the time. Okay? A lot of people try to say it the other way around. They say the true mean will fall in this interval. No. The true mean is a true mean. It is already there. It can't fall or not fall. No. You can have an interval that may or may not contain, but the mean cannot fall or not fall because the mean is already there. Okay, what is random is not the mean. The mean is already there, population mean. What is random is your confidence interval because you're taking it from a sample which you collect randomly. So the confidence interval is random, not the true mean. Get it? So this confidence interval, so today you do 8 plus or minus 2. Tomorrow you do an experiment, somebody gets 9. They do 9 plus or minus 2, so 7 to 11. That interval is 95% confident of containing the true mean. Make sense? That is the beauty of why we keep using the mean. Okay, and the other reason why we use the mean is Because if your sample is large enough, then most of the time your mean will follow a normal distribution. So you can do it that way. Yeah. So people that have heard me speak about this before, no, they know I like to use this riddle. Okay, which is, what does Pink Panther say or do when he sees a dead ant? Yeah. He says, dead ant, dead ant, dead ant, dead ant, dead ant, right? That's what Pink Panther does. He sees a dead ant. The question now is, what does Pink Panther do when he sees a live ant? How Ray live ant? How can he do same? Huh? What does he do? And he kills it first and then says dead ant, dead ant, dead ant. Yeah. So that is what we do in statistics a lot of times. We kill the ant to say dead ant. So what do? We take mean. Because now the mean is normal. So now I can do normal distribution. I'm very happy. Otherwise I have to do complicated distributions. Okay. So now with mean I can do normal distributions. If supposing the mean doesn't work, why do we use overall median survival? Because it is the data is very, very skewed. Okay. Alright. So what do we do there? We say no. I'm not going to use median directly. I can't just use average of median and say dead and. I can't do that. Okay. So what do I do there? I kill it, but I kill it with a little bit more trouble. Okay. I transform the data. Okay. I exponentiate it. I take logarithms of it. I do all these different things. And after I do these things, then I kill it again. Okay. And then do dadan. So when Sadhana talks to you about a log rank statistic, you will find out that that also follows a normal distribution only at some point. Okay. So a lot of times we do whatever we can to be able to get to finally the normal distribution so that we can do our testing framework in the normal distribution space. Everybody good with this so far? Yes? Yeah? So we started with population. What is a sample? Then we take a sample. We started with different types of data, but forget about that. That everybody knows, right? Then we said different types of, we take different samples. Correct? You don't take different samples. You do only one. But in the world, you can take infinite number of samples. Correct? And then we found out that if you take a statistic of the sample, like a mean or a median or something, okay, then the mean of the sample has this really nice property called the central limit theorem. So it follows a normal distribution. Correct? Normal distribution with the true mean being the original population true mean, which we don't know because we are not all gods, and the standard error being s over square root of n. Okay? With that, we construct a confidence interval, and then we can say with 95% confidence that that interval will contain the true mean. Okay? This is the basic framework that we use for hypothesis testing. Okay, everybody so far? Yeah, so let's quickly move to hypothesis testing then. Okay, so what happens in hypothesis testing? Okay, so basically, let's say that you are trying to formulate a new question. It's a new trial in breast cancer. You want to find out if drug A is better than drug B. But how better means what? Is it smaller, easier to swallow? Is it blue in color? I like the color better. Okay, does it make you live longer? Does it make your hair not fall so much? Yeah. Does it have other, does it make you sleep better? Like how better means what? Correct? So your hypothesis, and this is tremendously important because I've already seen some people writing their hypothesis as part of their protocols. Okay. It's not good enough the way you're writing it. Your hypothesis has to be an extremely clear formulation of the two assumptions. Okay. So your null hypothesis, which is what you hope to reject. Okay. Your null hypothesis is not what you want. Is the opposite of what you want. Okay, so your null hypothesis here says the response rate with drug A is less than response rate with drug B. Yeah, that's not what you want. You want to show A is better. Correct? So your alternative hypothesis is that the response rate with drug A is better than drug B. Okay, because in statistics, all the action happens on the null hypothesis. So you either fail to reject the null hypothesis or you reject the null hypothesis. Okay, if you reject the null hypothesis means this must be true. If you fail to reject it, which means I don't know, I don't have enough data to show that A is better than B. Okay, so all the action happens in the null. So the null is the opposite of what you want. Okay, this is marginally better, but this is still not fully okay, because your hypothesis response rate means when? After 1 week, after 6 months, after 5 years. So you can keep on looking, and one day when the response rate becomes better, like, yeah, stop the trial now. Not like that, right? So you have to pre-specify and say exactly when. You say response rate after 4 months of treatment with drug A is less than drug B or better than drug B. Okay, so that is a level of specificity that you need in your hypothesis. Okay, make sense? All right. So now that you have figured out what your hypothesis is, forget about all of these because we don't have time. Otherwise, if you had time, I would have given you a test. But now I'm not giving you a test. Okay. Okay. Now let us say so because what happens is, if you were treating drug A and drug B in the big population, in the entire population, okay, then you will never make a mistake. Because you treat everybody with drug A, or half with drug A, half with drug B, the whole thing is done and you're finished. Okay, so you know exactly what the truth is. But obviously that's not possible, no, because you don't know all the patients, you don't know the entire population, correct? So what happens is that you take a sample, correct? Like we did before. Okay. Now this is the entire population in the world treated with drug A, breast cancer. This is the entire population in the world treated with drug B. Okay, let's say the blue ones are responders. Okay, after 4 months. What is the response rate here? 80%. What is the response rate here? I don't know. Calculate quickly. 35%. Okay. All right. Which is better? Mostly 80 is better than 35. No, mostly. Most of the time. Yeah. Right. So 80 better than 35. So drug A better than drug B. This is if I could treat every patient with breast cancer in the world. So the entire population. Okay. But that's not what we are doing. Okay. So what do? We take a sample. So let's say we take a sample here. This is a sample we take from drug A, and we are very, very unlucky because this is a sample from drug A and this is a sample from drug B. Okay. Now what is the response rate for drug A? Not the lightly shaded one, the bright ones. That is your sample. Okay. So these are your sample. These people are not part of your study. Okay. So what is the response rate for drug A? 56%. What is the response rate for drug B? 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 5 by 4, 9, which is again 56%. So they are identical. So in your study, you will say, are drug A, drug B same? Because you were just very, very unlucky and chose the wrong population. Okay. So because you're taking a sample from the population, you can make errors depending on how your sample comes out. Correct? So what are the types of errors that you can make? Huh? Sorry? Yeah, that is sample selection is one type of error. But what are the types of errors that you can make? Statisticians are very, very good with English. Yeah, very good with English. So we have given extremely intuitive names. One is called type 1 error, the other is called type 2 error. Because you have two types of errors, okay? Okay, so what is type 1 error? Okay, so here, if you look at this decision tree, okay, your decision, this is a decision based on your sample. This is the reality, which only I know because I'm God. Okay, so you do not reject H0, and H0 is actually true. So this is correct. No problem here, no error. Okay, same thing with the next one. You reject H0, and in reality, the alternative is true. So again, no problem here. So these two places, no errors. Okay, the other two places, I'm rejecting H0, but in reality, H0, I'm rejecting H0, but H0 is actually true. So this is called type 1 error or alpha. Okay, and the other case, I'm saying I'm not rejecting H0, but actually H1 is true. Yeah, and that is called type 2 error. Okay, now what is alpha Alpha is not type 1 error. Alpha is a probability of making a type 1 error. Okay, it's called a type 1 error. That's the error you make. The probability of making that error is called alpha. Okay? Type 2 error is the error you make. The probability of making the error is called beta. Okay? Everybody gets it? Alpha, beta? Okay? Now, how can you find out what is alpha and beta? How can you find out? How can you calculate alpha and beta? See, you guys have not had enough coffee. You're not paying attention. What is one of the first things I said in the first 5 minutes? If it is Greek, you cannot know. That is why you say Latin and Greek. It is Latin and Greek to me, which I don't know. Correct? I cannot understand. Right? It is Greek, so you can never find out what alpha and beta is. You can never calculate alpha and beta. Okay? What you can only calculate is, you can try to control alpha and beta. Okay? You can get estimates of alpha and beta from the sample. But the true alpha beta you don't know, because reality you never know. Okay? So you try to control alpha and beta. What do you control alpha and beta at? Correct. Sample is good. Now, what do you control? What is the value of alpha that you would like to have? Alpha is making type 1 error, right? Rejecting H0 when H0 is true. What would you like for it to be at? 5%? Why? No, why 5%? No, 95%, but why 5%? Why 95%? Why not 1%? 99% confidence interval also you can have, no? Why do you want 5% alpha? For no reason, actually. Okay? Because poor Fisher, when he wrote this paper very long ago, he basically said, let's try and control alpha, say, at 5%. Gave an example there. Everybody said, Sade Fisher said 5%, we have to do 5%. So since then, we're doing 5%. So FD also said 5%. Yeah, so everybody likes 5% now. So we'll also do 5%. Because we don't like to buck the trend, no? We should do what everybody does, right? So we'll also take alpha typically at 5%. What about beta? Nobody cares. 80% is the opposite of beta, 1 minus beta. Okay, that is power. Okay, the 1 minus beta is power. I'll get to power. Power actually, Dr. Shrikant is going to do later. So he'll talk about power. He's very powerful. I'm not so. Yeah. Okay. So 1 minus beta is power, but beta is, you want it at 20%. You're very liberal. Take 20%. Yeah. He doesn't mind making type 2 errors. Why? Because he doesn't work for a company. Yeah. Because what is type 2 error? There's a probability of not rejecting H0 when H0 is false. Yeah, which means the drug works, but you're okay to say the drug is not working. So for him, it doesn't matter. He doesn't care. He doesn't own any pharma stocks. He says, make mistakes. Yeah, no problem. Yeah, but pharma companies are not like that. No, people that invest in, like I work in a pharma company. Yeah, I'm bothered. Yeah, mostly the FDA is also bothered because they want patients to get good drugs. Patients are bothered because if the drug works, they want to take it. Correct? But you depend. You basically say sometimes 20%, sometimes 10%. All depends. Okay, so beta is a little bit more flexible. The FDA mandates alpha a little bit more closely. Okay, make sense? So 5% alpha, 10-20% beta. Now, the problem is that can you make both alpha and beta small? How can alpha be 0? How can you make alpha 0? Huh? No, that's exactly very good. Excellent. Yeah, you just study the whole population, so no error. Brilliant. I'm glad you're paying attention. You've had good coffee. Yeah? What is the other way of making alpha 0? The large sample, no, that is full sample. Large sample still error happen. One is full sample. The other is, see, what is alpha? Alpha is the probability of rejecting H0. Yeah. So what if you say I will never reject H0, no matter what happens? I will take whatever data, but I will always accept the null hypothesis. The drug A is never better than drug B. So I can never make alpha. Can never make a type 1 error, correct? But then, if I do that, what will happen to my beta? Will increase. Similarly, the other way around, right? If beta I try to reduce, alpha will increase. Okay, so it's a trade-off, right? So how do you keep both alpha and beta small? Yeah, so what is the whole concept of hypothesis testing? That's when I'm going to go to my paint. Yeah, I'm going to start drawing. It will be terrible, but 1 second. ये खुला है ना? Okay, so this is what we're going to do. Okay, we're going to start drawing how null hypothesis, null populations, alpha, beta, how do they all work? Okay, so let's start with blue. Okay, we like blue color. All right, so I'm going to say first that, okay, I'm going to draw the shape of the distribution, sampling distribution under the null hypothesis. Okay. Okay, so under the null hypothesis, what is the value here? What is the mean expected to be? No, the mean value. We said that the sampling distribution, this is the distribution of x bar, correct? X bar. These are the values of x bar. Okay, or let's say these are the values of x1 bar minus x2 bar. Okay, I'm trying to find the difference between the two populations. Okay, all right, so this is a value of the difference between x1 bar and x2 bar. Okay, so under the null hypothesis, I expect what? That the two treatments are the same, correct? So which means what is the value of the mean under the null hypothesis? 0, yeah, very good, correct? So I expect this to be around 0. Okay. Now what I'm saying is I'm going to draw the same population but under the alternative distribution, under the alternative hypothesis, which means let us say that x1 bar is actually greater than x2 bar. Okay, so let's do that in red. Okay, so let's say this is how that looks. Okay, and then this is the mean. Okay, what would you like this mean to be? Take any number. 10? Okay, somebody likes 10, so I lose 10. Okay, everybody is good so far? So which means that if I get values close to this space here, I'm doing my experiment now. Okay, now I've drawn a sample, I'm calculating this x1 bar minus x2 bar. Okay, if I get values close to this area, what will I conclude? I will conclude the alternative, right? I will reject H naught, correct? So in this space, if my values are here, I will reject H naught, correct? If my values are here, what will I do? I will accept H naught. I will fail to reject H naught, correct? So which means that on this line, so supposing I get a value here, what will I do? Accept or reject? Okay, accept, let's say. If I get a value here, what will I do? Reject. If I get a value here, what will I do? Don't know. Don't know, no. Because it becomes tough, no? So at some point here, there is a threshold, right? There is some cut point, which basically you say that, let's say I'm going to draw this here. Okay. Why chumma? Okay. All right. And I'm going to say anything to the right of this, I'm going to reject. Okay. Anything to the left of this, we'll do that with blue. Anything to the left of this, I didn't work only. Okay. I'm going to accept. Sounds good? Yes? Everybody with me so far? Okay. So now tell me what is, okay, I'm going to do this. Tell me what is the value of this area. What is happening here? In that space where I've drawn the squiggly lines, what is happening there? That is a time when actually the null is true, correct? Because I'm still under the blue distribution. So in reality, the null is true, but I'm choosing to reject the null, right? So that is when I'm making a type 1 error. So that is a probability of making a type 1 error. So what is that value? This value is what? Alpha. Okay? Alright. Similarly, if I go to this side and I say this squiggly lines now. Yeah? What am I doing there? I'm under the red distribution. So I am accepting the null when in reality the alternative is true. So I'm making a type 2 error. Correct? Which means, what is this? What is this value here now? Excellent. Right? Because these are probability distributions, right? So this value is beta. Okay? So you see what is happening now. If I move this line to the right, what will happen? Alpha will become small, but beta will become large, right? If I move this line to the left, what will happen? Alpha will become large, beta will become small. Yes? Okay. So I can pick this line based on what do I want my alpha and beta to be. So if I want my alpha to be 5%, beta to be 10%, I can pick this line such that, right? But I may not be able to, correct? Because if I put alpha at 5%, this beta may already be at 20%. Okay. So now what should I do? If I want to make that 10%, what should I do? How can I make beta 10% when I put this line, it's already, if I put alpha at 5%, beta already comes at 20%. So what should I do now? How can I make this area smaller? Sorry? I can't move these two closer, right? Because this is a truth. This is at 10 and this is at 0. So I can't do anything about that, right? So how can I make these areas smaller? I can make them smaller by making these curves thinner, right? So what I can do is, I can say that instead of the curve being so fat, the curve can be like this, right? And I can say this curve now can be like this, correct? So now I've made the area smaller, even though I've not moved any lines at all, correct? How do you make the curves thinner? What are the curves? What determines the width of the curve? No, yeah, confidence interval, but what determines the width of the curve? Actually sample size, but actually what determines the width of the curve? Standard deviation, right? The standard deviation is what determines how wide the curves are, correct? How can I reduce the standard deviation? The standard deviation is what it is. I can't do anything to it. But what do we know about the standard error of the mean? What is the formula? S divided by square root of n. So now if I make my n larger, I can make the standard error of the mean smaller. If I make that smaller, the curves become thinner. If the curves become thinner, then my area is controlled. Okay. So that is why they say the sample size, okay, this is governed by these three things, right? There are three things that I can do here. One is I can either play with alpha and beta, but once I fix alpha and beta, if I want this to be the way it is, if I want my alpha and beta to be fixed, then the other lever that I can pull is standard deviation. Make sense? The sample size. Yeah? So this is how this whole thing. So this is what you do. So then you do your experiment. Okay. You do your experiment and find out. Supposing the value of your x bar is here. Then what will you do? Supposing you do your experiment and in your sample the value of your x bar is here. What will you do? Accept or reject? Reject the null hypothesis. Correct? If the value of your I'll do greens, yeah. If the value of your x bar is here, then what do you do? What do you do? You accept, correct? So that's all you do. So all of this is fixed. So this curves and sample size and all that is a design part. Then you run your experiment. You get your sample. You get a value of your sample. Depending on where it falls on that line, you either accept or reject. Okay. What is your p-value now? P-value is the probability of getting a value under the null hypothesis or more extreme than that. So this is your value of p-value. So for first time, when this is your value of x bar, your p-value is this green value. Okay? Now this green area, is it lesser than the blue or greater than the blue? Is lesser, right? What is the value of the blue area? Alpha, you have fixed it at what? 0.05, 5%. So if your green is less than 0.05, then you reject the null hypothesis. Okay? If your x bar was here, then what would this value be? The p-value is all of this green area. Correct? All of this green area is greater than this blue or less than this blue? Greater. So p-value is bigger than 5%. So if your p-value is bigger than 5%, you accept. If your p-value is lesser than 5%, you reject. Does that make sense, everybody? This is the whole framework of the hypothesis. Okay, so this is how you design your experiment. Okay, all of this stuff is how you design it, and then you get your value, and then you calculate a p-value, and you base it on that. Okay, so this x bar that you get, no, this is what somebody said was z before, which is a test statistic. Okay, so you can have different types of test statistics. Okay, if you have, let's say, if you want to test the difference between two means, that would be a t-test. Yeah, if you want to test the difference between two standard deviations, that would be an f-test. Okay, so the kind of test that you do depends on your data and depends on the hypothesis that you're trying to solve. But the underlying principle is just this. Does that make sense? Yeah? Okay. So what I'm going to do is, I know it's beyond 10:20, so I'm going to let Sadhana come in and do the rest. Okay. She's going to talk to you a little bit about survival. Okay. But if there is an opportunity, maybe during the break or something, okay, what we'll do is we'll take about 10 minutes more, okay, to talk about when do you use the different types of tests. Okay. When do you use a t-test? When do you do, when would you do regression? When would you do logistic regression? Yeah. So we can, sorry? I'll do it right now. Okay. All right. Okay. Then we'll just continue on. Okay. You guys are still okay, no? Still don't need coffee? 10 more minutes. Okay. All right. So this is the basic premise of how you do your testing. Everybody understands it? Okay. So what have we done so far? Population, sample, distribution of the sample. Okay. Therefore, coming up to hypothesis testing, alpha, beta, p-value. Okay. And when do we accept, when do we reject, what are the types of errors, and how do we go about doing that? Okay. So this is a basic framework. Now we move to saying, when should we use the test that we should use? Okay. So supposing, let us say that I have two populations. Okay. And I want to find out the mean difference between the two populations. Okay. What is the kind of test that I would use in that setting? Yeah, some of you that are familiar with it? No? So you would use something called a t-test. Okay, what is t? T is a test that was designed by a guy called Student. Actually, his name was not Student. He used to work for a beer company. Okay, and he used to write papers, but because everybody didn't want to know, the company didn't want everybody to know that this guy was working in their company, he wrote under the name of Student. So it's called a Student's t-test. Okay. So if you have x1 bar, okay, let us say you have the mean of all students in, let's say, division A versus the mean of all student scores in division B. Yeah, you want to find out whether division A is smarter than division B. You take the mean here, x1 bar minus x2 bar. That is called a t-test. Sounds good? Yeah? So in this case, what do we have in, so when do we use a t-test? We use it when we have two classes only, two levels, class A, class B, and we want to find the difference between class A and class B. Okay, that is when we use a t-test. Okay, there is another version called a pair t-test. When you don't have a class A and class B, you only have one class, but you want to say what is the mean score of class A before the teacher teaches and what is it after the teacher teaches, and hopefully it will be better, right? So now it's the same set of students. Okay, so what do? You take the after score, subtract the before score, okay, and then you get a paired t-test. Make sense? Okay, so t-test is when you have two levels, yeah, and you want to find out the difference between those two. Okay, so what is your response variable here? What are you measuring? What is your outcome variable? Score. What is the value of score? It's a number, right? So it's quantitative. Okay. And what is your class variable? Qualitative, because it's division A and division B. Make sense? So if your class variable, your explanatory variable is qualitative, two levels, and your outcome variable is continuous, numeric, then you use a t-test. Okay, please write that down. Because I don't have a slide for that. I'll make a slide and I'll send it to you guys. Okay? Make sense, everybody? Okay? Now, what happens if instead of two classes, two divisions, you have three divisions? You have A, B, and C. And you want to find out if all the three divisions are the same or are they different. Then what would you use? Three or more. Yeah? You would use something called an ANOVA, right? Because again, your outcome variable is continuous, numeric, but your explanatory variable, your class variable is categorical with three or more levels. Exactly. So class here is not generally that class. Here is division A, division B, whatever. Class variable is essentially saying, what is your input variable? What is your, so you want to find out your explanatory variable, right? You're trying to find out, are the divisions the same or are the divisions different, right? Okay, and your outcome variable is a score. Make sense? Yeah? Okay, so this is when you use a ANOVA type of thing. Okay, now let us step away and say, what happens if my class variable or my explanatory variable itself is not division A, division B, division C, but it is, let us say, it is what is the age of the student. Okay, so you want to find out if the age of the student has an impact on the score. So even within a particular class itself, are the older students doing better than the younger students? Okay, so now what is your input variable? Age, which is continuous, right? What is your output variable? Score, which is also continuous. So in this setting, what would you use? No. What would you use in this setting? In this setting, you use a regression frame. Okay, you use linear regression because you're saying, does the age have an impact on the score? Make sense? Okay. Exactly. Correct. Yeah. But in this case, what happens is your scores are normally distributed. So you can directly use regression. Okay. In the survival setting, the survival is not normally distributed. Correct? So you can't directly use regression. You use a different type of regression, which Sadhna will talk about. Still regression, absolutely correct, but it's not directly simple linear regression. Yeah, because you use simple linear regression when your outcome variable is normally distributed. Okay, everybody. So we did three things. Okay, input variable is class levels with two levels. Output is continuous. What do you do? T-test, not student. Student. Okay, so T-test. Yeah, your input variable has more than two levels. Outcome is continuous. What would you use? ANOVA. Yeah. Your input variable is also continuous. Your outcome is also continuous. What would you use? Regression. Linear regression. Simple linear regression. Or multiple linear regression. Whatever. Yeah. Good. Everybody okay so far? Okay. Now let us switch tracks and say what you want to find out is two outcome variables which are both at two levels. Okay, which means, do people smoke? Yes, no. Do people have lung cancer? Yes, no. Yeah, so you have a 2 by 2 table. Yeah, in this setting, what would you use? Something like a chi-square. Yeah, because now you're trying to say that your input is class, your output is also, your outcome is also a class variable. Okay, then you would use a chi-square. Okay, now let us say that you now say that you want to find out if you still have, your outcome is still whether you have lung cancer, yes or no. So your output is still, your outcome variable is still categorical. Okay, yes or no, two levels. Okay, but your input variable is continuous. Let's say it is number of years that you were exposed to asbestos. Okay, so you worked in a mine. You know that when you work in a mine, you get exposure to asbestos. That also causes lung cancer. Right? The number of years that you were exposed to asbestos is your input variable. So it's a continuous variable, but your outcome is a categorical variable. Yes or no? Do they have lung cancer? Yes or no? What would you use in that setting? Huh? Fisher? Imagine that your input variable, whenever your input variable is continuous, in the previous setting when your input variable is continuous, what did you use? Regression. So here also use regression, but you don't do simple linear because your outcome is binary, yes or no, correct? So what do you use here? Logistic regression. Because your output is yes or no. Okay? If your output was skewed like survival data, okay, then you would use a different type of a regression that Sadhna will talk about. Okay? But anytime your input variable is continuous, you're always looking at a regression framework. Whether it's simple, if you have survival yes or no, okay, then you're going to use a different test, which also she'll talk about. Okay. So if your survival is yes or no, and your input is, let's say, uh, whether they got treatment yes or no. So now it's a 2 by 2, but it's not a direct 2 by 2 because your survival yes or no is not just a 1 or 0 because you're taking years of survival and so on, right? So then you use something slightly different because now your input is class, your output is, so instead of a t test, you use something called a log rank. That setting, so everything remains the same from the basic framework. Your input is a categorical variable, your input is a continuous variable, and so on. Make sense? So we talked about logistic regression, when you would use logistic, right? And the last part is about survival, which I'll let Sadhna do. Okay. Now the idea is that depending on all of these different tests, whatever you do, the basic testing framework remains the same. Okay. So if you were to do a, let's say, a t-test, ultimately your t-statistic, you will do something very similar here. Okay. If you were to do a chi-square test, for a 2 by 2 table, ultimately the chi-square test will look something like this. The alpha, beta, p-value, all of that remains exactly the same. If you were to do an ANOVA, you would do an F test there. The basic testing framework remains the same. Okay, so this is the basic testing framework. Once you understand this, then it's simply a question of what method should you use and what is the corresponding test statistic that you should use. And for that, you should come to either Sadhna or me because then otherwise we won't have jobs. Right? Okay, but once you understand what is happening behind, then it becomes really simple because then somebody will come and say, actually, you can't use this. You should use a logistic regression here. And you know why. If you were to do a logistic regression, what would you do? The logistic regression has a model. Okay, then there is a coefficient there, beta naught. Okay, beta naught, that coefficient, no, beta 1, that coefficient, testing. You're basically testing to see if that beta 1 is 0 or non-zero. That testing framework remains the same. Exactly like this. Okay. So irrespective of what test you use, a testing framework is this. Okay. It's just what is the kind of test that you use depending on what is your data, what is your outcome variable, what is your input variable. Good? Simple? Continuous means it can either be decimal, but you can continuous essentially means that it's not fixed numbers of levels. So you can take your age in, I want to be either 10 years to 15 or 20 or 25 years, right? So it's not a fixed number of levels. That's all. Yeah. Traditionally, continuous means you're allowed to use decimals. If you want, you can do decimals as well with age. Yeah? But even if you have discrete integers only, but you have it over a very long period, like more than 10, 15, 20 levels, then you can treat it as continuous and it works well. I'm sorry? Actually, that's the beauty, right? Kill it and then say da-dang, da-dang, right? You're right that most real data is not normal, but once you take and transform it, it becomes normal. Yeah, so the log rank statistic that Sadhna will talk about, where your outcome variable is is skewed, survival type, with censoring and all that. Yeah? That also, once you do a set of things to it, it becomes normal. Logistic regression. Okay, what you're doing is you're using a function called a logit on your proportion of success. Yeah? Proportion of 1 or 0. So you use a log of p over 1 minus p. That's a function you use. Once you use that function, that becomes normal. Non-parametric is completely different. Okay, anything that you use, survival or survival is non-parametric, but anything else, chi-square, f, all of those kinds of things, they may be not normal, but they may still be parametric. Okay, but once you move to a non-parametric setting, what you're essentially saying is, I cannot assign a distribution at all, whether it's a t distribution or an f or a chi-square. I can't assign any type of a distribution. Yeah? And frankly speaking, non-parametric things, even though you actually say you're doing non-parametric. For example, let us say you do a Kaplan-Meier. It's supposed to be non-parametric, but ultimately the log rank statistic use a parametric assumption to do the test. Those are the only ones, but those are very small. You would do that if your sample sizes were very, very small. Yeah? Good? All right. I really have to give it to Sadhana now, otherwise you're not going to do anything on survival. Yes, sorry. One last question and then I'll give it to you. You could, but you will lose information. So for example, if you say that you have age and you have 25 values of age, but then you say I'm going to do less than 30, 30 to 60, greater than 60, you're losing a lot of information. Now what is the difference between 40 and 50? Now you have pooled them all into one. Any which way you do it, that's what I'm saying. Ultimately, you're going to lose some information. So you could do it if you wanted to, and in some cases there might be a good reason to do it, but generally you would not. Correct. Everything. That's a basic rule. Anything you plan to do, mention in protocol. Otherwise, you can't do it. Okay, good. I am around for the rest of the afternoon. I'm there for the sessions of the mentoring sessions in the afternoon as well. Yeah. Okay. Good. Thanks, guys.
Thank you very much, Dr. Iyer. I have not seen a more elegant presentation of measures of central tendency and hypothesis testing. So thank you so much. Okay, so moving on, I would like to invite Mrs. Sadhna Kannan. She's the chief statistician at the ACTREC Tata Memorial Center. And she actually needs no introduction because she is well known to most of you, because I'm sure more than half of you are from Tata Memorial Center, and you would have approached her one time or the other for statistical help. And once again, she has keen interest in teaching. She also is in charge of the postgraduate diploma in biostatistics at ACTREC. And of course, some of our students are also here. So she'll be talking to you about survival analysis, which is a very important component of the kind of data that you usually generate in cancer, and the analysis that you will have to do. Welcome.
Morning, all of you. While they are connecting, I just want to say a few things. First of all, thanks to Mahesh for introducing these Greek and Latin errors. They're actually Greek and Latin when you start reading about type 1 and type 2 errors. Even our statisticians feel so. It's very difficult to understand, and he has put it so well in the clinical point of view, in clinical research point of view. When you take a question, convert it to hypothesis, and how to test it. Amazing talk, and especially it was so rhythmic. His example, which he often did, and is very nice. Very nicely he takes it. Thanks to my team. And so what we thought was, I'll be covering level analysis. Felt the Cox regression gained by him by starting the session early tomorrow. We are requesting him to touch upon the Cox regression. Very important.
Uh, yeah, so I'll be taking you through the survival analysis topic for the next 45 minutes. So by now we are familiar with, how to convert your research question into hypothesis and how do you test the hypothesis, the framework you have understood. And he briefly touched upon the tests which are available for different types of data, so which will help you in deciding what method to use in your protocol. And now I'll just start with the research question. What do we do in clinical research or clinical trials? We are doing it to assess the efficacy of new treatment regimens, right? So how do you assess efficacy? Especially when you're kind of treating the patients, you follow the patients, after they are treated, and how long you'll follow till an event occurs or till the study period ends, right? So typically in statistics, we'll ask for outcome variable. Here in this context, the outcome variable is the survival time. So it's a time which we are measuring. So we'll learn about what time and other things are. And it is measured as, time till an event occurs. Okay, this is what we do when we have a question, like when you're looking at what is the efficacy of a treatment, right? Now, what are the key questions we ask in that setting? So what we ask is, how long the patient survived after receiving a treatment? That is a major question, right? And the second thing is, if you're going to treat on one or more treatments, you ask, is there any difference in the survival pattern of those who are receiving treatment A versus B? Yeah, and we also would like to ask few questions, further, that what are the factors which are predicting the survival? The factors could be patient-related, treatment-related, disease-related, whatever be it. What are the factors which predict the outcome or the survival, right? These are some of the questions which you ask, for which conventional methods will not help you to analyze this data. We'll see why. Now, we have to analyze using, the data using a survival analysis. So what is survival analysis? It is a statistical method for analyzing the data where the outcome is time until occurrence of an event of interest. It is easy to write it, but it is very difficult to measure this time because there are a lot of problems in measuring it. So literally survival means whether they're alive or dead, right? That is what we look at. So most of the times in the context of death, it is called as remaining free of a particular event. That is why survival analysis. We don't restrict to death alone. There are several outcomes which we'll see. It's also called as time to event analysis or failure time analysis. So coming to the outcomes or endpoints in the oncology context, we know that we have overall survival, progression-free survival, disease-free survival, relapse-free, time to progression and time to next treatment. PFS2, progression-free survival, 2. Many of you will have this kind of an endpoint. So you should know how to define these endpoints, which is shown on the next column. And it's mostly a clinical definition of endpoint. So I'll just skip this. Okay, so always survival analysis is used in the context of alive or dead or the recurrence, progression and all, but they are used in other outcomes also. Positive outcomes also we can use, like if you're looking at normalization of WBC count, okay, if it can be applied, you can use that survival analysis for in this context. Other examples include HRT and first thrombotic episode, survival time of a heart transplant, time from marriage to divorce, time to change of a job. All these also can be analyzed using survival analysis. So now let's learn what time means. Time is nothing but the length of follow-up until the event of interest occurs. So when we talk about duration, we should have two dates. So what are those two dates? There should be a start date and there should be an end date. So start date is typically, if it is an RCT, it's a date of randomization into a clinical trial. Okay, and or it could be a date of surgery, chemotherapy or radiotherapy, whatever be it, you have to define it clearly. In a transplant setting, it's a date of transplant. If none of this, if you're working on a retrospective data, when you don't want to see any of this, then you look at the registration date sometimes. So it depends. So this who will define, it's a clinician who's going to define this, right? So what would be the start date? So you have to be clear. Now, what is the end date? We know that we are going to follow the patients until the event happens. So obviously the date of event is the end date for those who experience the event, and those who did not experience the event, it's the last follow-up date. Okay, typically measured in days, weeks, months, or years. Now, what is so peculiar about this kind of data? We follow the patients, until an event happens. But how long you're going to follow up? So there is a study period, study duration. So during that follow-up period, do all the patients, you know the status of the patient? You may not know. Some of the patients are kind of, you don't know their status, right? They don't experience the event, you don't know what happens to the patient. So this type of, times are called censoring times. And what is censoring? When the event of interest is not observed for whatever be the reason, so we don't know the exact survival time in those patients. So they are censored. So most commonly used censoring is, there are different types, left censoring, interval and right censoring. The most commonly used censoring pattern in oncology is called the right censoring. It occurs when a patient does not have the event of interest during the study. Like you kind of follow them and you don't know what happens during the follow-up. Common reasons of right censoring include patient did not experience the event of interest. It could be relapse or death before the study ends. Patient can withdraw from the study due to reasons like ADRs or anything, and a patient is lost to follow-up during the study period. Okay, it could be patient experience a different kind of event due to which you could not do any further follow-up. So these are some of the reasons for censoring. So what are we going to do? How are we going to handle this data? Because not all of them are kind of followed up in the specified time interval. So if they have been followed up, you can use a conventional methods. So to understand censoring a little bit further, I'm just giving you an example here where there are 6 patients. Okay, so if you see the first patient, and we all know that we don't enroll the patients on the same day. Patients, it's a staggered entry. Patients keep coming at various time points. So here I show you the first patient who has entered the study, and that patient has experienced the event in a very short span of time. Okay, the plus symbol indicates an event, and the circle, unfilled circle, is a censored time. So the second patient also has joined the study in some part of the time and experienced the event. The third patient, if you see, the patient has been followed up for a longer time till the study ended, but the event has happened after the study period has ended. Okay, so as for the study or end of the follow-up date or the cutoff date, whatever you call it, the patient is censored because you have followed for that particular time and the patient has not experienced the event. And the fourth patient also has been followed up for a long time and the patient has experienced the event. And fifth one, the last patient, I mean, after some point of time, we did not know what happened to the patient. Okay, he's not into us. I mean, you could not follow the patient up. So the patient is then censored. So what you know is in that period of time, you know the patient is alive. Right? After that, we don't know what has happened. Okay, so these are the times we capture and we analyze in our survival analysis. Now, as I said, all patients don't enter at same time or same day. So it's a staggered entry, which is a study date is different for each patient. And you convert the this time into a follow-up time where, you know, whatever be the start date, what is the duration of follow-up till the event or whatever the last follow-up date. So that is how all patients' times are captured, how you kind of from the calendar time to the follow-up time. Now, analysis of time to event data, how do we analyze? It poses two major challenges which we cannot use because of which we cannot use conventional methods. The time interval can vary from, you know, subject to subject, and also at the end of the event, you know, at the study, event may have occurred for many subjects. Okay, so time is actually not normally distributed. As Mahesh said, it's not normally distributed. Okay, so if it is normally distributed, then you can look of some methods or, you know, to analyze such data. It is not normal. In a long follow-up time, many subjects drop out. Okay, so that's where the censoring comes. So these two things pose challenges to analyze. So the conventional methods, what are the disadvantages? We can think that, you know, why can't we compare the mean survival time, whatever be it? We have two groups, the survival times of two groups, take the mean value because time is continuous. So take the mean values and compare, you know. So what will happen? If you can use a t-test or any regression methods to compare, but what happens? It ignores censoring. When you compare such mean times, we are assuming all the patients are followed up for the, you know, the study period time. So, and then that is not right actually, right? So it will ignore censoring. And if you decide to compare the proportion of events, okay, let's not worry about the time. Let's see how many events happened in, you know, arm A and arm B. If you want to compare, there you're ignoring time, right? So that is the problem, you know, which is posed with the survival time data. So that is the reason why conventional methods could not be applied to analyze the time to event data. Now, what are the statistical methods to analyze time to event data, which we'll be seeing in detail? Generally, when we have any data, we just do a descriptive statistics, or then we move on to some univariate, so-called test and all that. So in this time to event data, we kind of, you know, do describe the survival pattern using a median survival, or you can also, you know, quantify using proportion surviving at any particular time point. You can further on move on to, like he said, regression methods, like in order to see what are the factors which contribute to the survival pattern, whatever, if you want to compare and all that. So you can use a Cox regression, you know, so which we are planning, Mahesh will be covering in detail tomorrow. So in multivariate analysis or a Cox regression, what we do is we come up with an effect measure called a hazard ratio, right? So that is what we use to describe the survival data. Now, what is the Kaplan-Meier estimation? So the Kaplan-Meier method is named after Edward Kaplan and Paul Meier, who each of them submitted their manuscripts in JASA, and they were asked to combine and come up with a new, you know, one publication. That's where the Kaplan-Meier estimation came. So what is a Kaplan-Meier estimator? It actually calculates the survival probabilities at each time interval in which an event occurs based on a conditional probability. Conditional probability is you're calculating a time probability at a particular time. It's conditional to that they have survived the earlier time point. Okay, so cumulative survival over the entire follow-up period is derived from the product of the interval, all the intervals, like, you know, and the survival probabilities are plotted on the Kaplan-Meier survival curve. You will actually see how to draw the curve in the next few slides. So after you do the analysis, this is how we represent the Kaplan-Meier curves. It is always a step down curve. Okay, every step down means some event is happening in that time point, and you can compare two, you know, curves or so, and we represent using this kind of a graph. Now, what is log rank test? Whenever we want to compare two curves, we use a test called a log rank test. The test compares the curves. So null hypothesis is the curves are statistically same. Now alternatives, they are different. How it does is you compare the observed and expected events, and then the test statistic to compare that is a chi-square distribution. Now log rank statistic by formula, it is O minus E the whole square by E. I mean, if you're comparing the two groups, one for treatment 1 and the other is for the treatment 2. And O1 and O2 are the observed events for treatment A and B, and E1 and E2 are the expected events for treatment A and B, which you will see how to calculate the expected events. Then you plug in those events in the formula, then you will be able to calculate the log rank test statistic. And it's like how you test any other hypothesis like t-test or anything, you test this value also. That is how you kind of draw an inference whether you will reject or you do not reject. Now I'll give you a small example of hypothetical data, and I will show you how a Kaplan-Meier curve can be drawn. So this is an example of time to progression among the patients with NSCLC. There are 38 patients in this group, and all patients were followed up for 2 years till time to progression, and the event is progression here. This is the actual raw data. Okay, so if you see, it's spread over 4 columns. First column is the time in months. So 1 to 24 months is the data which we have, survival time. And the next column is the status. Status means what happened to the patient during that time, right? So it is 1 means progressed, 0 means they have not experienced the event till that time. Okay, so I will take you through how to draw a survival curve now. So what we do is, the beauty of Kaplan-Meier curve is you calculate the probabilities at exact times, unlike your life table methods where you have intervals, and there are a lot of other assumptions related to life table method. It's also called as actuarial method. We don't do it in that way in clinical context, but it's very difficult for us to assume that things. They are typically used in an insurance setting and all, right? So here, if you see, let's start with the first month. So what happened in first month? If you see the data here, we have how many patients? 6 patients, right? And what happened to the 6 patients? Yes, they all had the event, right? So what happened in the first month? We started off with how many patients? 38, right? So what happened here out of 38? 6 of them experienced the event. So how many are without the event? 32. So they are the ones who are surviving, going on to the next interval. They are at the at-risk set for the next time point, right? So out of 38, 32 are what? Event-free, right? So what is the proportion surviving at the end of time 1? It is 32 upon 38, which is 84.2%. So can you see the curve has actually stepped down at time point 1. Okay, now we'll move on to the next part of the curve, this is called the survival probability, which you typically get along in a Kaplan-Meier curve table. You get a table data, that is what it is, and I'll show you how it works. Now let's move on to the next time point. Next time point, how many individuals were there? 32 were there actually. How many experienced the event? 5, right? So how do we calculate that? We are going to calculate the conditional probability, right? And we are going to take the cumulative survival probability. So what we do here, how do we calculate? So what was the earlier proportion? So 84.2% of the patients have survived 1 year, because if you want to calculate, 1 month, if you want to calculate for 2 months, it's subject to survival of the first month. So in the second month, how many patients have been, this thing? Out of 32, 5 of them developed the event, right? We have only 27 out of 32 who are going to the next time point, who are without the event, right? We are going to follow them up, right? So 27 out of 32 is 84%, subject to the earlier 1 month they have survived, right? So that is 84.2 into 84.4. So 71.1%. So the curve has come down further, right? So at time point 2, the survival probability is 71.1%. Now let's move on to the third month. So what happens here? We have how many events happening? And how many are at risk? How many are starting this interval? Yeah. So what do we do in this case? How do we calculate? Same way. So we have, right? So if you see why we have taken 26 instead of 27? One patient is censored also, right? So we have 27 minus 1, out of which, there is 3 patients had experienced the event. So 23 are remaining risk-free, or they have not developed the event, right? So 23 upon 26. So that is 88.5%, right? If you just plot these probabilities, you will not get a proper curve, right? So this is subject to surviving month 1 and month 2. So if you calculate that, then it comes to 62.8, because 84.2 was for the first month, 84.4 the second month, then 88.5. This is the conditional probabilities, then you kind of multiply it and you get 62.8. So the curve has further dropped down, right? Like this, you move on calculating for each and every month, and finally you can see this curve, right? This is how the curve is plotted. Now, can you see some asterisks on the curve? What is it? Yes, they are the individuals or the patients who were censored. They were available till that time point. We did not know what happened to them, so we have kept them till that time point. These are censored, which are marked in asterisks there. Okay, so this is how you kind of plot the curve. Okay, and the same thing if you do using a software, and most of you use SPSS. So I just took it as an example. You can use other softwares also. So what you do there is you kind of put the time variable in the time call slot, and you have the status. Status is what? It is always you define the event as 1 and no event as a 0. Then you kind of put in that variable there. Then you get the same table. If you see here, what do you see at month 1? 84.2%. That is what we did it in the handheld calculation also. Now month 2, what happened? 71.1% were surviving. So that's what you got here. Additionally, what you get is a standard error calculation, because you need to use it for getting the confidence interval. All that can also be worked out to some extent. So this is how you will interpret your the table which comes out of SPSS. This table values are kind of plotted. Additionally, you will see here a small table where you total number of individuals who have been considered for the study 38, and number of events 25, how many were censored 34%, all that. And if you see, this is how the curve looks like when you use SPSS. It's exactly the same as what we have done manually. So along with it, you will have the mean and median survival time. Mean survival time is nothing but the the area under this Kaplan-Meier curve, and the median survival time here for this you will learn about it later. Median survival time for this data is 6, and the confidence interval is 2 to 9. Okay. So this is what we do it, how to do the basic calculations. The same thing applies if you're comparing 2 or more groups. So I've just taken another data where you kind of, if you want to compare treatment A and treatment B, it's a very small data I've taken. 15 patients, 7 or 8 are in treatment 1, and the rest are in the treatment 2. And the outcomes are given here. So in this data, what we do is we do the same calculations as we did earlier. Okay, I've just shown it for one of the treatment, which is treatment 2. Okay, all these similar to what I have shown in the earlier one, the NSCLC data. And you calculate the cumulative proportion and the proportion surviving and make a table like this, and you do for both the curves. This is after using it in SPSS, you can get these kind of curves, which is what I've shown you earlier. And what do we do now? We have the 2 curves now. What is the hypothesis, or what is the question we're asking? Whether they are different or not. How do we test that? Which test we will use? Log rank test. Yes, log rank test is what we will use to compare. And log rank test, what calculations we do in log rank test? We compare the events, right? Observed and the expected events. So we know observed events, we see it at what time point, how many events are happening. But the expected events, you have to kind of do a bit of calculations here. I mean, you will have I've just did for one group. This is all 15 patients data, which has been shown here. You have a column with number known to be alive, right? Okay, initially we start with 15, and as the event occurs, we start kind of, goes down. You have the number of events happening at each time point, and the risk of death is calculated. Like if you see in the first case, it is 2 deaths out of 15 patients, right? So the risk of death is 13.3% there. Okay, and here I'm just doing for one group, so which has 8 patients. So number known to be alive in that group is 8 initially, right? I apply the risk of death to that group and I calculate the expected number of events, right? So similarly, you do it for all time points for the next group also. If you sum it up at the bottom, if you can see E2, it is nothing but the expected number of events in group 2, because all this calculation is for group 2, right? So the expected number is 3 here, right? So you compare the observed and expected. So you do the same for treatment 1 and then plug in this formula, right? O1 minus E1, the whole squared by E1, plus O2 minus E2, the whole squared by E2. So you know how to calculate E1 and E2. You have O1 and O2 in your hand. So just plug in and then you just calculate the chi-squared value, and you know how to infer. What Mahesh has shown you how to kind of get the p-values and all this applies here also. Only thing is the different way we use, to calculate the test statistic, which is a chi-squared here. Now, this is how you get it in software. You will get the log rank test value, which is a chi-squared value, 5.682, degrees of freedom 1, and the significance is 0.017. So how do we interpret this? If you see the curve, no, we don't interpret using a chi-square value, right? Chi-square is just telling you whether there is any difference, right? Like he covered in the morning, what happened, what do you do with the t-test, what do you do with the chi-square test. Here, there is no, if you really want to quantify the magnitude of difference, you have to use your hazard, right? This only tells you whether these curves are different, right? So don't interpret the chi-square value in terms of fold difference or how much it is, better or worse, whatever it is. It just tells you that, yes, there is a difference in the survival pattern of these two groups, right? That's all it tells. It just gives you an idea about the groups. That's it. So further on, you want to really kind of, you can add an effect measure like hazard ratio and then kind of interpret the data. This is just like a univariate, you want to know whether which are the variables, whether treatment have made a difference or not, that's it. Now, coming to the confidence interval, this also you can calculate, and I'll just take you through how to calculate the confidence interval. There are different methods to calculate. Okay, so you have the time, you have the number at risk and number of deaths happening at each time point. Then you know how to calculate the survival probability, and you take the use this formula, deaths upon number at risk into number minus risk minus deaths, and you sum it up because it's a cumulative data. So you just sum it up and then you kind of multiply by the survival probability. This is a simple formula. So, and then you use it in your calculations for, getting the 95% CI. So what you get here is SE of the survival probability, which for any confidence interval, the formula is what? Estimate plus or minus the reliability coefficient, which is 1.96 into standard error of the estimate, right? Here, what are we estimating? We're estimating the survival probability. So you have the standard error of the survival probability. So plus or minus 1.96 gives you the confidence interval. So now, many a times we get the data in Excel. This is our experience among our statisticians. They will all agree. They are not properly structured because the data is what you people give us the data, right? So you have to know how to kind of arrange the data. So please have the, the data arranged properly so that, even whether you do or we do, it makes our life easier, right? So you have to have the, this is a transplant data I've taken. So you have the date of transplant, date of last follow-up, right? And what happens if you're looking at the overall survival, you have to define the events, whether it's alive or dead. I typically use 1 as the year event and 0 as the no event, right? And you can have many outcomes also, like I have RF is also coded here. So what you do is you always get the date of death, right? And sometimes in one column, last follow-up date, you bring date of death, date of last follow-up, everything happens. So keep the date of death separately and date of last follow-up. And, so then you kind of, merge it together for this, when you're looking at the OS data. And that's how you have one date, because The starting date could be, as I said, any of those RCT date of randomization or registration or start of treatment. End date can be kind of coded, you can have the dates like this, but make sure that you follow up adequately, and then you can put the last follow-up date, okay? So every time, like, it goes back and forth when we analyze it, update few patients, and again the next day we'll get update of another few patients, so it becomes very difficult for us to analyze, and for you also. So after you kind of add the follow-up data completely, then you can go in for the analysis. And how do we report the results of Kaplan-Meier curve or the survival analysis? There are few tips which I kind of give you, because we may be calculating many things, but we don't know. Good journals always demand for these things. So it's better to learn how to report whether it is good or a, high impact or a low impact journal, whatever be it. Follow consistency. Why this consistency has to be there? If you maintain this, whenever we do a meta-analysis, so it is easy for us to, if you're combining studies, if one study has not reported HR, one study has given Kaplan-Meier curve, one study is not given, but they are given in words, it's difficult for us to, actually I reconstruct the data and I kind of calculate my HRs. It's it's possible, but it's very painful. So whenever you represent your results, please make sure that you add all these things in your curve or results, whatever you kind of report. So first thing is the median follow-up time, and the second one is a median survival time. And you can also report the survival rates at any specified time. We'll discuss about that. And for example, you will see 2-year, 3-year, 5-year, how to decide, we'll see. Kaplan-Meier curve with number at risk table is very important. SPSS doesn't give, but from the big table which I have shown, cumulative events, you can nicely make a small number at risk. So that is possible. And lastly, the hazard ratio with 95% CI if you're comparing two curves, okay? Now, what is the median follow-up time? So median follow-up is a time at which 50% of the patients, have been followed up, right? And you know what is happening to that, right? So we know data is censored, so median follow-up is a very important indicator in order to know how mature your data is. So anyone who looks at your Kaplan-Meier curve or Cox will always look at, first find out what is the follow-up time of this group, then accordingly they'll be able to appreciate your results, right? So median follow-up is very important. It tells you how mature your survival data is. How do you calculate that? So there are 3 methods. You can use all patients, the median time, or you can use alive patients, or we can use reverse Kaplan-Meier also to estimate the median follow-up time. But if you see, typically this is how it is. You can see all patients will have lesser than alive patients, and then lesser than the Kaplan-Meier, reverse Kaplan-Meier method. It all depends on when and how the events happen, and what is the follow-up time and all that. So the next is a median survival time. So median survival time is what? You draw the curve, right? So what is your y-axis? Yeah, so median survival is 50%. If you just go across the curve, right, and come down, then you can get the time. So that is the time at which half the subjects have died and half are still alive, right? So it is easy to, read from the curve itself, right? So that doesn't mean we should not report. Always report the median survival time also, okay? Now, finally, having learned all these important reporting matrices, how do we kind of make sure to represent on the curve? This is an example which I have shown you. This is a curve, Kaplan-Meier curve. If you see, the first one is your median follow-up. We don't write it on or mention it on the curve. We just write it in the text. The second one is your median survival time. Right here, it's a progression-free survival is the outcome. So you can have the median survival time, right, reported. And they also have reported at 10 months what happened and survival rates. 24 months survival rates have been reported. It's always good to give how many events happened and how many were randomized, right? So it will be easy for, as I said in the meta-analysis, or if anyone has to plan any further studies, to get an idea of your, data. And of course, hazard ratio, right, with 95% CI. And more importantly is your number at risk, So your curve will be interpreted along with your number at risk and other indicators, okay? So it's important to report all this when you're, whether the journal demands or not, you can always report these indices. And finally, as I said, this will be covered at length by Mahesh. I think he's the right person to cover this. So I'll just touch upon this effect measure, because we all know how to draw a survival curve. We understood what it means when you have a sensor data, and how to calculate all the important matrices for reporting the survival data. Lastly, like you said, when you compare, you cannot use a chi-square statistic, right? You can never use a chi-square for effect measure. We have to use a measure called hazard ratio. What is hazard? Hazard is an instantaneous event rate. It is the probability of an individual who will experience an event, any event, it could be death or progression, whatever it is, at a particular given time point, assuming that that individual has survived to that particular time point, right, without experiencing the event. So when you represent the hazard of the two groups, then you kind of calculate a ratio. If you want to compare one relative to the other, we have to represent using a hazard ratio. It's nothing but the probability of an event in treatment group relative to the control arm. It's a probability again over a unit of time. This ratio is called an effect size when you measure the time to event data. Okay, so use hazard ratios to estimate the treatment effect in clinical trials, and whenever you want to assess the time to event data. So hazard ratio, as I explained, it is intervention over the control. Okay, so how do you interpret a hazard ratio? Hazard ratio, can be interpreted for, the risk as well as for the protection. So if you see the line, if you see a line, vertical line, that is the line which is drawn when you say a ratio. When both the treatment and the control groups are at equal risk, you expect it to be a ratio to be 1. So that is a null value, okay, whenever you're testing a hazard ratio. So I mean, across the null value, you see how your treatment effect falls. If it falls on the other side, it says that, if it's more than 1, it favors the control treatment. If it is less than 1, it favors the intervention, right? Because what is the formula of hazard ratio? It's treatment over the control, right? So you expect the events to be, if the treatment is efficacious, then you kind of see the events happening lower in the treatment arm as compared to your control arm. So the ratio will be less than 1. So if you get a ratio which is more than 1, then it is going to be favorable for the control arm. And if it is less than 1, it is going to favor your intervention arm, right? So how do you really say that the hazard ratio is, significant in terms of confidence interval? Let's say if I get a hazard ratio of 0.78 and the confidence interval include, say, like, 0.6 to 1.02. Is it significant? Of course, you will get a p-value when you kind of do all the calculation, but you should be able to understand what it means. Why? If it is not significant, why? Yeah, the confidence interval includes null value. So any confidence interval based testing, if you're kind of, estimating the effect, always make sure that the null value is not included in the interval. The null value depends on the question you're asking. If you're comparing means, there the null value is 0. If you're comparing, ratios and, relative risk, odds ratio, hazard ratio, the null value will be 1. And you have to see what the null value in the context of your effect measure. Okay, so in this case, I'm just giving you an example here. In the results, the authors have reported that the hazard ratio of death with the new treatment is 0.38. Okay, 95% CI is 0.28 to 0.53. P-value is highly significant. So what does it mean? How will you interpret? Yeah, of course, treatment is effective. So if you see here, at any point of time in the treatment group, 62% are less likely to die, than the patients in the control arm. How did we get this 62%? Yes. Okay. And, we are 95% sure that the true value will lie between 47 to 72%. Right? How do you get this? Yes, so you convert it in terms of the, if you really want to say that, in terms of either risk or benefit, this is how you kind of switch over and then you interpret. As I said, if the confidence interval of HR, if it doesn't include 1, then the HR is significant. Okay, so we don't use log rank test statistic to compare the, in order to say, how many times it is better than, or how you cannot use it as an effect measure. So please. Yes, yes, yes. Yeah, yeah, yeah. Yes, yes. So now, I think this is my last slide. And finally, he will cover in detail tomorrow. It's about Cox regression and like any regression methods. So here for time to event data as an outcome, we use Cox regression for survival data. And like he said, for linear, you have continuous outcomes, and for logistic, you have binary outcomes. For time to event, we have to use a Cox regression. And here, outcome variable, which is actually a censored survival time, and you'll have some predictor factors. It could be anything patient related to, all those factors you can study to predict the survival. And finally, you kind of use an effect measure, which is the hazard ratio. And that is all I wanted to cover. Thank you all. I can take questions, if any. Yes. Can you give me an example? Yeah, if you're defining it as an event-free survival, define your events. Then it becomes an event-free survival where your event is death or progression, whatever it is, that you will have to define. Yeah, yeah. See, it depends on what is the disease, under what setting you're treating, what would be your endpoint, which will be valid and all. Any other questions? If no questions, thank you all. Yeah.
Okay, thank you very much, Sadhna. So we come to the end of the morning, the first of the morning sessions. Okay, so we are going to break for tea, but please remember we are already 15 minutes late. So I would request all of you to finish your tea in quick time. I don't think you will be able to get tea here, but finish tea in quick time and come back in next 10 minutes for the exciting talk by Dr. Bangdiwala, because he will be talking about a lot of things, including statistical analysis plan and sample size calculation, which is most, in the sense, it is the most important topic from any researcher's perspective. So please come back in 10 minutes. Okay. but at the request of Dr. Dennis, who will be talking about the stress and other aspects of junior doctors and the textbook that he has written about how to manage that. So, what do you think?
Um, okay. Okay. Um, Good morning, everyone. I'm just going to take a few minutes to tell you something that is very different, but very important. And thank you, Dr. Vikram, for this opportunity to spend a few minutes on this. In 2015, I was made the first Vice Dean of the postgraduate program at St. John's. And even in a very good institution like St. John's, we didn't have a program or activities for well-being for postgraduate students. So we initiated multiple activities or events for them, and some of which are still continuing. I finished my term there, and one of the things we did is to bring out a book. So I want to tell you this. So I'm sure all of you agree that junior doctor time, whether you're doing your MD, MS, or MCH, DM, is a critical time both professionally and personally, and it's also a very impressionable time for these people. They could end up either being disillusioned or really inspired during their training. So to ensure they are less disillusioned and more inspired, we developed two strategies for them. One is a book, a toolkit that we produced, and I shared a copy with Dr. Vikram. I have one copy, I can show it around to you. And we also set up a 2-day well-being workshop for them. Yeah, yeah, we can share that later. And so this is how the book looks, and it has these parts here, which is one is on academics, then life in the hospital, and then the really important one is beyond academics, which is self-care strategies. So just a few things on hospital, night duties, how to talk about death, and how to learn from your mistakes, how to handle difficult people and patients, and even violence, legal issues. All of this, in some institutions, they have a very good orientation program. They tell them well, but sometimes there's not much time for that. So we thought we'll put it into a little book like this. But the really important section here is self-management, or beyond academics, self-management, mental health, when to seek counseling help, right? Work-life balance, peer support, role of family, personal relationship, how to be a good mentee, so on and so forth. Okay, so this is not a sales pitch. Nobody makes profits out of this. Of course, there's a publisher, and there is a cost to making the book. So this book is priced, it's available in Amazon, but the publisher has made a commitment to us that any profits, after all the costs are covered, any profits will go into a well-being fund for well-being initiatives in the country. So one of the initiatives that we already started are these well-being workshops, and these are customized topics. We've already begun doing these workshops. We've done 5 of them, including CMC Ludhiana to places in Hyderabad, Bangalore, and we are in discussion with other institutions as well. It will be for 1.5 days, and the topics will be customized, not no lectures or no heavy stuff, but about 40 to 60 students sitting together with some of their own faculty. We have about 12 topics that we have chosen from here, which will be good to discuss. And at the end of it, we come up with some strategies. And the students so far have been quite happy. Firstly, they tell, one day we got a break from doing our routine work. And one of the feedback they thought, for the first time in our life, we are thinking about ourselves and our well-being. So we firmly believe if the junior doctors are not well, the patients will not be well, they will not get better, the society will not get better. And I don't have to give you statistics about the worst thing that can happen, which is young doctors taking their life. So you can look up the MCI or NMC website for details on the number of young doctors who died by suicide. So my colleague Dr. Suhas was a psychiatrist, and the one line inspiration we had is let's do whatever it takes to save one life. So details about this workshop are there in the book, and this is available on Amazon for you. You can also contact the publisher directly, for, they're ready to give it to you at cost price, that is printing price, plus whatever packaging and distribution charges. So thank you very much for this opportunity, and I hope we can meet again to talk about our own well-being. Thank you very much.
Thank you very much, Dr. Dennis, for taking this initiative to address the well-being of our junior doctors who are the workforce of any hospital. And I wish you all the best with the book and all the workshop that you want to conduct moving forward. And moving on, I would like to next invite Dr. Shrikant Bangdiwala for his much anticipated talk on sample size and statistical analysis plan. Dr. Bangdiwala focuses his expertise in the statistical analysis of longitudinal, multi-center intervention and observational studies. As lead statistician on several NIH-funded randomized controlled trials and longitudinal cohort studies for over 35 years, he has had the experience of collaborating with several statisticians in developing and conducting the statistical analysis plan for multi-center studies. He is presently the director of biostatistics at McMaster University, Canada, and he has earlier held the position of professor of statistics at University of North Carolina. Welcome, Dr. Bangdiwala.
Oh, yeah, that's good. Okay, so much anticipated talk because everybody's always stressed about necessary. So first of all, I would like you to relax, don't be stressed, and think about the fact that sample size estimation is an inexact. So people worry that, oh, my statistician told me I needed 254 patients in my study. I have 248. This is not going to work. No, relax. We will see that when we are doing the calculations for sample size, it really depends on a lot of assumptions, a lot of uncertainties on parameters that go into the calculation. So it's very inexact. Now, there's a big difference between 20 and 200, but not between 20 and 22 or 250 versus 240. Just relax about it. Let's go through this. Yeah. Okay. So what we talk about necessary sample size, we have to know for what. Most of the time, at the end of the study, we want to have what we call adequate. And Dr. Mc already talked to you for is, and what inputs are needed to calculate the necessary going about. But there's not all studies involve samples related to. I wanted to say that in some cases, we don't have it because sometimes we're not interested in testing it. Sometimes we're interested in estimating something. What is the proportion of people that get cured on portion of individuals that do better? Not usually maybe comparing. That's typically what we do. Clinical trials do always want to test the Dr. Mahan. We are null hypothesis. There do need to look at, but sometimes, especially in observational studies, we may not be comparing groups. We may just be studying what is happening, what is the, in a cohort study, we're looking longitudinally of how many people develop something. Now we're just estimating that, we're not necessarily comparing. But when we are not comparing groups, then we're estimating, and now we're not talking about the power that I have, it's the precision that I have in my confidence intervals. And I'm going to say maybe the proportion that get better is 40%, plus or minus what? How wide is your confidence interval? Does it go, if say 40%, it goes from 10% to 70%, That's very imprecise. You say 40%, but it goes from 35 to 45. Now you're more precise. And to get a more precise estimate or tighter confidence interval, what you need is larger sample size. It's the same thing. We will see that for more power, you need, as was illustrated very nicely with those figures, you need to do it by increasing your sample size. So just to make it clear, we have a distinction between sample size for power and sample size for precision. Whoops. Now, in all cases, there are aspects that will affect that calculation, and they're going to be statistical aspects and non-statistical aspects as well. Otherwise, okay. So I just wanted to get some examples. Here is a phase 3 two-arm superiority trial that was actually conducted at the Tata Center, looking at patients with head and neck cancer and suitable for cyplastin-based chemoradiation. And in the PICO format, they looked at radiation with concurrent dose tassel and radiation alone, and looking at 2-year disease-free survival as their outcome. Okay. Now, it's hard for you to read that. So on the next slide, I have there that they had 356 participants. And so the question is, why 356? Where did they get that? Was this what was needed? Or was this what was possible? Is this sufficient? Where did they come up with this? Well, you look in the method section, and they do say how they did it. They have to specify what they believed was a 2-year disease-free survival of 40%. What was the target effect in the hazard ratio? Then, as Dr. Sadhna said, you are now wanting to see that its intervention is better. So you wanted a hazard ratio. In this case, they wanted 0.756. They chose a type 1 error rate, and you now know what a type 1 and a type 2 error rates are, right? And they chose a type 1 error rate actually quite big. It's not that 0.05 two-sided. They took actually a 0.1 one-sided. So that's a 0.2 two-sided. So people can be flexible. You have to justify how you do it, depending on how much you will tolerate that making that type 1 error. Are you willing to tolerate it as much as, in this case, 10% one-sided? It's an arbitrary thing, actually. Most people go with the type 1 error of 0.05 because most people, unfortunately, believe that it's a magical number. And as Dr. Mahesh said, it is totally ambiguous. And it's because Fisher found it convenient to use that back in 1923. 100 years ago, somebody thought it was convenient, and everybody has believed that that's magic. So it's not. So we will see exactly how it does. So when you increase it, you will not necessarily, if you're able to tolerate more error, then you do not need as much of a sample size. We will see, and the same thing, if you tolerate more type 2 error, which means having less power, you will also not need as much sample size. We'll go into that, because this is just an example. So then they calculated that this was a disease-free survival. So the variables or the inputs needed were given, and then it's an event-driven one. But they had COVID-19 impacted recruitment. So now we had statistical considerations to determine how much sample size they needed, but now you have logistical, practical reasons that impact your sample size, and they were not able to get it. And so they ended outcome, which was overall survival, and their power that they had there was considerably lower. 600. And many, not all. They 91 people. Then, was this what was needed? Was this what was possible? Was this sufficient? This is when you read a paper, you need to say, why did they do this? Is this an appropriate sample size? Some of you, you're at the planning stage, but when you are looking at somebody else's, you need to think about that. They state in their statistical analysis section, as this was a retrospective analysis, there was no formal sample size calculated. That seems strange because they actually were comparing two survival curves. So they should have had it for the survival curves because they did the log rank test. And they ended up, this is very slow somehow. Wow. Have to catch it this. So they ended up, if you have a very small sample size, you end up with very wide confidence intervals for their estimates. So they're doing an observational study. They're not supposedly not testing anything. And so therefore you would provide the precision of your estimates of median overall survival. And they have it for two groups, those that were getting some adjuvant chemotherapy or neoadjuvant versus those that were getting palliative intent therapy on the left side. And you see that the confidence interval for the median overall survival, which I added this red block down at the bottom, is extremely wide. So then when you start talking about it, it becomes that people don't believe your results. So you have to have an adequate sample size for precision, even if you're doing an observational study. They actually, I think it's because journals love p-values, they ended up comparing now something that was not in their primary hypothesis because they said it's an observational study, but then they checked the median overall survival in months between 3 different groups. And because the adjuvant therapy did so much better than the neoadjuvant and the palliative, they were able to show significance. Okay, so these are just 2 examples of what we think about, that the results of studies, whether their significance or not, is driven a lot by the sample size. And that is why we worry at the design stage in designing the study with the appropriate sample size so we're able to reject the null hypothesis when we should be. Okay, so what to consider for sample size depends on whether you are comparing groups, which is now you're testing, and that usually is what we do in a randomized controlled trial, but we also do it in observational studies. Groups that are exposed to something and groups that are not exposed to something, we want to compare them. And we may not be randomizing them, we may not be intervening, but we are observing in what's happening in some population. In an observational study, typically we are estimating something. And so in these situations, we have to either look at power considerations or look at precision considerations. And this is the important step, is that you as the investigator decide how much power you want. Don't ask the statistician how much power they want. Because as Dr. Mahesh said, we're always powerful. Investigator also decides how much precision they want. Do you feel comfortable reporting the overall survival, median survival with those very wide confidence intervals? Or you want to report it with narrow confidence intervals? How narrow do you want it? You decide that. Don't ask the statistician for that. All right. Now, what I'm going to do, because we don't have so much time, I'm going to concentrate on when we're comparing groups. So we'll talk more about power than on precision. And I'm also going to concentrate on randomized controlled trials, because most of the talks have been on randomized controlled trials. So we already know this. I'm going to go very quickly because Dr. Mahesh has already talked about this, the idea of statistical hypothesis testing. We usually have a claim, and the claim can be of superiority, non-inferiority, or equivalence. More commonly today, we usually do superiority or non-inferiority. And the claim is what you want to show. And so that is your alternative hypothesis. The status quo is, if you don't have that claim, is whatever you have currently. So usually the typical one for superiority is that their status quo or the null hypothesis is there is no difference between active and control, while the claim is that the active, for example, is better than control. So what is the process? We already know it, so I'm going to go there. What we do is we get evidence, and for superiority, we want to see which evidence is consistent with the null and which evidence is consistent with the alternative. And as he so clearly explained, when you get a small or negative difference, you're consistent with the null of no difference. And if you have big positive differences, you're consistent with the alternative of difference. This is the opposite in non-inferiority, because now you want to see that the difference is consistent with the null if the difference is not too negative, while consistent with the alternative of non-inferiority is that the difference is not too negative, and therefore you can claim non-inferiority. The question then becomes, how small is small for determining that the difference is too small, or how big is big? Or in non-inferiority, how much difference is tolerable? Again, these are values that you as the investigator determine, but they will affect your sample size. So this I'm not going to go over because he's already gone through this. We're very clever in coming up with names like type 1 and type 2 error. And you know what is the correct decision and what is the incorrect decisions. We want the probability of type 1 error to be very small. That's the alpha. I like to make the analogy of saying that the truth is, if somebody is accused of having committed a crime, we usually, all courts in the world, most of them I think, assume that you are innocent until proven guilty. And innocence is the H naught and guilty is the alternative. You're being accused. The claim is that you're guilty. So the truth is you're either guilty or you're not. But the decision of the court is either we have found enough evidence and we believe that you're guilty. So then we reject the innocence and claim that you're guilty and say that you're guilty. But we never accept the null hypothesis. We say not guilty. We don't have enough evidence. And the same analogy comes in here. Now, alpha is very small because that's similarly or analogously to saying that somebody that's innocent is guilty and now we're going to send them to the gallows or do something to them bad. We don't like that to happen. And so typically we go with this 0.05 magic number. And we want the probability of type 2 error to be small too. But as you saw very clearly before, is that if alpha is small, then beta gets bigger. If you want to make it one bigger, the other one gets smaller. But we're willing to tolerate letting a guilty person go away than a little bit more than we are to put in an innocent person in jail. So usually, typically, we don't want it to go beyond 0.2, so a power of 80 or higher, okay? So power is the probability of this correct decision. Now, when we're choosing the sample size, as I said, there are statistical aspects, and we'll go through those, but there's also non-statistical aspects. The statistical aspects involve your type of outcome variable. If it's binary, if it's a time to event, if it's a count, like number of episodes of, or number of relapses, or number of sites that are metastasized, or whatever. If you're counting things, whether it's a discrete thing, how much pain do you have? Mild, moderate, severe. People do different types of outcomes. It's not always time to event like disease-free survival or relapse-free survival or whatever. So if it's an event, we look at event incidence, and the formulas for it are going to be different. But there's things that are common to all of these, and those are Greek letters, as was mentioned earlier, right? These are parameters that are not known, and we have to estimate them. So we need to know the variability, that's sigma squared. We need to know how much we are willing to tolerate for type 1 error, and that we specify usually 0.05. How much power we want, then we specify it, 80, 90%, whatever it is. But here comes the crucial one. How much difference do you think there is between the null and the alternative? How, if they're talking about effect size, this is how much better do you think is your treatment than your control? Everybody would like it to be very big, but you want to go for the smallest meaningful difference. And this is something that you decide in discussions with the statistician, and that's that you want to detect a difference of little delta between the null and the alternative. There's also how many tests you're doing. We usually do one test in a randomized control trial. We do multiple tests many times in other situations. But those are the statistical reasons. Then we have basic study design aspects that are going to affect it. Do you have only 2 interventions or you have more than 2? We're doing a multi-arm study. Now we have a little more complicated calculations. We do a randomized control trial, 2 parallel arms. What if you do crossover or you're doing factorial? How are you doing your randomization? Most of the times, simple randomization. No, but you want to do it stratified. You have to do it by cluster because this is an intervention that is administered at a clinic level, or it involves training physicians or nurses to do something. Or it may be multi-stage. Now you're complicating things. And people say, I have 1 primary outcome. No, I have 7 primary outcomes. Well, you have now multiple primary outcomes. You have to increase the type 1 error, or no, you don't want to have it go up. So you have to adjust for that. So usually we have 1 primary outcome. And number of important strata. I want to look in this group. I want to look in that group. I want to look in this strata. Those are things that complicate things and increase your sample size. Okay? Then we have things that almost many people forget about. And these are study conduct issues that now are going to impact your sample size needed. How many people are not going to follow stuff? Do you know? If your intervention is it has side effects that are terrible, people are not going to follow. People are not going to want to do some things that are difficult to do. Or people may want to choose the one that they were not randomized to. They'll cross over if it's possible to do. Some things they're not, but some things they can. How many are going to drop out? How messy is your data? How incomplete? How much incorrect? Missing outcome? Quality of the data. Most people assume data are perfect. No, that's wrong. Data are always imperfect. And what does imperfect, poorly measured data do? Increase variability. And we'll see that variability is the problem here, because increased variability will mean that you will need a larger sample size to deal with it. Okay, so this is the one slide you have to remember. When you want to look at power, there are 5 numbers, and they are interrelated numbers. And you can wait to take your picture later. You get the slides, don't worry. Alpha, we all know now, is the level of evidence required to declare significance. We know power is the likelihood of declaring I have a significant result if one exists, right? You had that in the previous lecture. Delta is the difference between treatment you wish to detect, the noise in the system, or the variability. And this is very important. That's the variance that you have. All these 4 are going to impact and determine the sample size. Okay? And now the question is, sometimes you are limited on sample size because, wait a second, this is a rare disease. The most I can get is going to be 50 people or 200 people if I do it multi-center, et cetera. And there is a relationship between these 5 things. If you remember in your high school, when you took classes of algebra and you had a formula that had 5 things in the formula, and you gave 4 of them, you could get the 5th one. So now I have 5 things, and we usually specify those 4 to get the sample size. But I could go the other way. And I said, oh, wait a second. I can only manage from budget or from practicality this sample size. Oh, then let me backtrack and see how much power would I have with that sample size, with everything else fixed. Or I want this power and I have that sample size. How much difference can I detect? Right? So you could actually play around with it like that and present it that way in your protocol. So this bottom formula is a conceptual formula. Don't put any numbers in this because that doesn't work. This is for you to understand how these 5 things are related. That says the more power you want, if you want 90 versus 80, you're going to require a larger sample size. because it's in the numerator. The more variability you have, the more noise in the system you have, you're going to require more sample size because it's in the numerator. The smaller your significance, if you want to go from 0.05 to 0.01, then you will require more because it's in the denominator. Now, in that previous example, they went higher. They were willing to tolerate a type 1 error of 0.1. So therefore, they got a smaller sample size for that. Because when you make it bigger, then the sample size goes down. The crucial element here is the difference to detect. Because what? It's squared. And it has a really big impact on your sample size. So if I believe optimistically that my study is going to show that this intervention is so much better than the existing intervention, that I don't need a big sample size. But if I want to be realistic and not optimistic, and I put in a small number there because, oh, I'm going to improve a little bit, now I'm going to require a big sample size. And then people play around with it to see what can I manage from a practical standpoint, because I just cannot get 20,000 people or 2,000 people. I can only get 200. Then what is the difference that I can detect, or how much is the power that I'm going to have? So every formula for power is like this one conceptually. The actual calculations, they're books and textbooks. When I was a student back in the dark ages, in the 1970s, we had books with formulas, and we had to find the formula appropriate for our design and work it out by hand. Nowadays, we have software. So we don't have to. What the software will calculate it. It's built in properly. The formula is there. What you need to know is this, that this relationship is what's happening in every one, whether you're doing logistic regression, or you're doing the Cox model, or you're doing a log rank test, whatever you're doing, all of them are conceptually exactly the same. Now, just to mention that for estimation, it's different. We're not going to continue with this, but in estimation now, the sample size determines on how much confidence you want. Usually you want 95% confidence intervals, but that doesn't change. How much noise I have, the larger the noise, the more sample size, but how precise I want, how wide will I want my confidence interval to be. The narrower I want it, since it's in the denominator and it's squared, that is what makes the impact and makes it bigger, okay? But we're going to talk more about power than precision. Okay, so just to show you an example, depends on which software you have. We use PASS, power and sample size, PASS. I think the Tata Institute, as Sadhna said, they use the same one. Some of these are, this is a costly one. There are things on the web that you can use, but beware, user beware. Things on the web are not things that necessarily have been validated or verified by anybody. And so you may, for simple things like comparing with a t-test or doing the log rank, maybe they will be good. But if you have a complex design, if you have very, stratified or whatever, you're not going to get it on the web, okay? You have to get, this is when you talk with your friendly statistician, and you'll get results. So I just wanted to give you some examples. If I wanted to compare proportions of events that occur in a specified period, now I'm looking at the risk of getting something, and I'm comparing the risk in one group, risk in another. I have a risk ratio. And what I have to specify are those things that I said that you have to specify, right? So I have to specify the power that I want, the 1 minus beta, the alpha that I want. I have to specify then the what is the ratio that I expect, so that will be what I want to detect, and what is in one arm and the other. Okay, very simple things to do, and that's all you have to do, and you'll get the calculation. But if I'm looking at, like most of you are doing, is the disease-free survival or overall survival, you're looking at a time to event data. Now you have a little bit more complicated things that you have to specify. or you can ignore. So the design there is going to be, again, you have to specify the beta, the alpha, and now I have to have the proportion surviving in one arm, the hazard ratio I want to detect. Then I have to say, what is my unit of time? But then I have to deal, accrual time. How long is it going to take for me to do the accrual? Because as soon as I start getting one patient, that patient is now being exposed. And so if I have a very long accrual, things may be impacted. And then the total time of follow-up is the accrual plus the total study time. And then I have these issues like how many loss to follow-up I'll have in the control arm, how many loss to follow-up I'll have in the treatment arm, how many people will switch from control to treatment, how many will switch from treatment to control. How do I know these things? The literature may or may not have it. These are guesses. These are assumptions. Hopefully you have a pilot study. Hopefully you have colleagues that have tell you this. Hopefully there's some experience in your institute among your colleagues. You get some idea about it, but you don't know. And so some things you can do is you may not even know what is the proportion surviving in the control because maybe there haven't been good studies on this. Or maybe you don't know, is my treatment going to really be good because the phase 2 studies did not really give me, there's some phase 2 studies that gave me very different results. So what should I choose? Well, you can, some softwares may or may not allow you to put multiple entries in it. Others, you have to do it one at a time and do it. So this one allows you multiple entries. And this is the example that I did for the binary one. I said, what if you have to specify the proportion in the control that are going to get the event and the relative risk you wish to detect. And so the proportion, I varied it from 0.4, 0.5, 0.6. And I said, what is the relative risk I wish to detect? And so for an effect of 0.75, 0.8, or 0.85, the 0.85 is closer to 1. So the closer I am to 1, the difference between the risk in the intervention and the risk in the control is very small. So therefore, the blue line here is very, very high. I need larger sample size when that difference is small. So here, the relative risk reduction is only 15%. If the relative risk reduction is 25%, which is the red line, red curve, I don't require as much of a sample size, okay? And for a relative risk reduction of 0.2, I get the green one in between. And then what do? Then you choose what can you manage budget-wise, practicality-wise, patient-wise, what you can recruit, etc. So you get an idea by doing not only one calculation, seeing how your input into the calculation, how sensitive is sample size to these inputs. Because many times you don't even know the correct input to put in. And so now I know that, wait a second, if I wanted to hope for a huge relative risk reduction, then I will be able to do a small sample size. But what if I do a small sample size and because I hope to get a big relative risk reduction, but I don't get it. I get something that I would have been okay with, but now I'm underpowered for it because I did not do it. So this is sort of the game that you do when you're designing your study. If I guess this example now is for the disease-free survival, for example, or time to event outcome. And I'm presented in terms of hazard ratio, as Sadhna mentioned, and you all now know about hazard ratio, is the hazard of the intervention to hazard under control. And here I specified, again, some different values for it. I had the hazard in the control of 0.55, 0.6, or 0.65 is the red, green, and blue. And the hazard ratio is going from 0.75 to 0.85. And what we see is that the hazard rate in the control, its sample size is not too sensitive to that. So if I did not know it well from the literature, I'm okay because it doesn't, choosing among those is not a big deal. But what really matters is how much effect do I think my intervention is going to have? If I'm going to have a very small effect, the 0.85, I require over close to 3,000 people. But if my effect that I'm going to get is big, then I only require around 800 people. And this is the kind of stuff that you have to think about when you're planning your protocol. You need to not do one calculation. You need to be checking how confident I am with the inputs that I'm putting in to the calculation. Let me vary those and see how sensitive that calculation is towards the necessary sample size. Now, that's the basics for sample size. That's it. Now, but there's complications. That is, we've talked about comparing to groups, looking at it for superiority. And there are other types of hypotheses. We could have a non-inferiority one or an equivalence one. And what happens? The hypotheses are different there. What the difference between the null and the intervention is interpreted differently. In the superiority one, it's looking at the smallest clinically meaningful difference. In non-inferiority, it's the maximum tolerable difference for non-inferiority, and in equivalence is the maximum tolerable difference for equivalence. And so usually these values conceptually, to show that something is superior, you'll have a small delta, but to show that it's not inferior, the capital delta is usually much smaller than the little delta, and equivalence is even smaller than the non-inferiority one. So remember that the difference between the null and the alternative is in the denominator of that conceptual formula. And so therefore, the sample size required for superiority is much, much less than a sample size for non-inferiority, and which is less than the sample size for equivalence, okay? So that's one thing to understand, that the type of hypothesis you have will impact your choice of the difference and therefore the sample size. Now, how you do your randomization is also going to affect it. Most sample size formulas that you'll see, most free software that's out there on the web assumes you're randomizing simple randomization. You have 200 people and there's 100 are going to go here and 100 are going to go there by flipping a coin each time, and you'll get until you get to 100 and 100, and that's it. Simple randomization. But if you don't do simple randomization, then the formulas are not as simple, and people don't want to program it and put it for free in the web. People that program it charge for it. You can get it in SPSS, you can get it in SAS, you can get it in Stata. For some things you have to get dedicated software for sample size. So stratified randomizations is when you first group them into mutually exclusive strata or groups, and then you randomly assign within each one. And this actually lowers your standard errors, so that's good, right? Lower standard errors give you higher power. So stratified randomization is often preferred, but the formulas now you have to do that with a dedicated software. Sometimes you're forced to do cluster or group randomization because your intervention is not done at the individual level, but you're randomizing clinics to do a certain type of procedure to all of their patients. And when you do group randomization, you have to consider what's called a design effect, which often gives you higher standard errors. And the design, so therefore, does the method of randomization affect the variance? Yes. And if you do some restricted randomized allocations or even blocking or permuted block, stratified, matched, optimized randomization, you would get lower sample sizes. If you do group randomization, you get higher sample sizes. But then why don't we worry so much when we do the blocking? What we tend to do is that we conservatively ignore it when we do stratified randomization. We know we gain in power and can reduce sample size if we wanted to tweak it, but we conservatively ignore it and just go with a slightly higher sample size. With cluster ones, we have to take into account the fact that there's that correlation or design effect. And how we do it is by inflating the sample size so that we calculate what's called the intra-class correlation coefficient, which quantifies how much correlation there is within a group. And now you have to take that intra-class or intra-cluster correlation coefficient and take the sample size little n that you've got and multiply that by this design effect. And the design effect is taking that estimated intra-class correlation coefficient, multiplying it by the cluster size minus 1, and adding this. So this number is always greater than 1. The only time it's 0 is that when any one of these are 0. So there's no correlation, or there's only groups of size 1. But always then you'll get an increase in it. That's why we typically don't like to do cluster randomized trials. We do them when we have to because the intervention is designed that way. I don't think in our group, at least, nobody was doing a cluster design. So I'm not going to go into the examples, but there are ways. I have some examples here and you'll get the slides. You can look at them. So that gives some examples on the effect on sample size to do it. Let's skip this part. Okay. So aside from the type of randomization, there are other adjustments that we have as well. Okay. So as I mentioned before, these are ones that are from the conduct of the study. How much you expect of incomplete data by loss to follow-up, or how much missing outcome data you're going to have. This is a very problematic issue because what do you do if you're missing outcome data? You don't know what people's pain score was or level of satisfaction with their chemotherapy was, or you were not able to measure whether they were alive or dead in a 2-year period because they disappeared. So typically, we prefer that our primary outcome not be a measurement or an observation. So if we don't get the data measured, what do we do? We can't do in terms of treatment. What we typically do is have as a primary a time event to deal with censoring. characteristic. But if I'm in, and that will be nice to do. But of how do you do these sorts of things. But having multiple primary outcomes does usually increase your sample size. What do we do about secondary outcomes? Well, are you going to test them? The general feeling is that among statisticians is that secondary outcomes in a randomized controlled trial are there for you to see if there's consistency of the overall result in these other secondary outcomes, also in the subgroups. But what I said is to see if there is consistency. See. I didn't say to test in each one of those. If you're testing in each one of those, then you have to power for it and you have to adjust for the multiple testing. Many people ignore that. They shouldn't. If a reviewer may criticize you if you do that. What you should be doing is presenting the confidence intervals and interpreting them not by saying it's significant in this subgroup, it's significant in that subgroup, but by saying we see consistency of the overall results in these subgroups. That's the terminology. You don't use the word significance in that term because not what you're doing. If you're exploring, you report confidence intervals and avoid claims of significance. But if you're testing, then you better calculate power and adjust for the multiple testing. So finally, on sample size, the type of outcome variable determines the sample size, right? Because the type of outcome variable that you have will determine which test you will have to do, right? If you have a continuous or interval scale 1, you'll be comparing means usually with an unpaired t-test. If you do not think that the distribution is bell-shaped and you don't have enough large sample size, you may want to do one of the non-parametric ones like the Mann-Whitney that is looking at the quantiles like the median, or you may want to compare the shape of the distribution. Many few people do this because the Kolmogorov-Smirnov test is not very powerful, but it's a possibility. If you're looking at an ordinal scale, you may then be looking at Fisher's exact test or an approximate chi-square test. If you're doing binary, it's also Fisher's exact test or a approximate chi-square test. If you're doing time to event, which is what most of you are doing, it would be the log-rank test. Those tests are very simple. The analysis, and we're going to talk now about the analysis in a clinical trial, that many people are disappointed when you go and tell them that analyzing the primary hypothesis of a clinical trial is the simplest, most basic analysis there is. It's extremely simple. Because what? You've controlled all potential confounders by randomization of a large number of people. You've designed the study so that you've standardized the inclusion and exclusion criteria. You've homogenized people, so there's very little noise. You've randomly allocated the distribution here of those confounders that are known, and the unknown confounders are balanced between them. You don't have to control for them. And you are under intent to treat. You don't do any adjustment. It's the simplest analysis. That's the primary analysis of your primary outcome in your trial. It's one of these simple tests. That's it. Now comes the other things that people do, and we'll talk about that in the statistical analysis plan. But for sample size, the type of outcome variable determines which test, and so therefore different tests have different power, and this impacts the necessary sample size. So for example, the unpaired t-test is in small samples, is very powerful if the data are bell-shaped. But if the data are not bell-shaped and you have a small sample, the t-test is actually very much less powerful. People assume that the t-test is more powerful than the Mann-Whitney test always. That's not true. In small samples, if the data are not normal, the t-test is not as powerful as the Mann-Whitney. The Mann-Whitney in large samples is approximately 0.93 of the power of a t-test. So it's not that so bad. People discard it. Fisher's exact test, people think is less as powerful. Actually, the chi-square test is an approximation. The Fisher's exact test uses the chi-squared statistic. It just calculates the p-value exactly. The chi-squared test uses the same chi-squared statistic that the Fisher's exact test uses, but it calculates the p-value approximately. So I personally prefer the Fisher's exact test because I want the exact p-value, and I rarely use the chi-squared test. The log-rank test, the same thing. It's approximately you can calculate the exact p-value of the log-rank test. There's ways to do it. It's called a permutation principle, or you can do, it's approximately in large samples, a chi-squared with 1 degree of freedom. So this is when you talk to your statistician, and the statistician will advise you as to which is your proper test. But keep in mind that different tests have different power, and it'll impact the necessary sample size. Okay? The softwares have this all built in. You don't have to worry about it. So I wanted to end the thing on sample size by noting that in randomized controlled trials, we usually focus on having the necessary sample size for the adequate power for testing what? One single primary hypothesis in your primary outcome. Not for testing multiple hypotheses, not for testing multiple outcomes. It's one hypothesis on your primary outcome. If you're measuring disease-free survival at 2 years and at 3 years and at 4 years, you have to choose one as your primary time point at which to evaluate your primary outcome, okay? So the sample size depends on the method of random allocation. They call it randomization. And usually the statistical considerations, like, you usually do the 0.05, usually do 90%, you don't go below 80%, and you are regulated by regulators as to what you should choose for different types of hypotheses, especially like non-inferiority. In observational studies, we don't have all these regulations. There's usually multiple objectives in each research questions, and protocols are usually not subject to regulation. And so if you have 3 or 4 objectives, what should you do? You don't have to have a primary one. You don't have to have a secondary one there. But you should follow the guidelines. If you have multiple objectives, you have multiple hypotheses, then you are testing multiple things. You better keep in mind that I may have to adjust for alpha because I'm doing that. Change the alpha because I'm doing multiple independent tests, but using the same data. And here, the sample size depends on the method of random sampling. It doesn't, because you're not allocating anybody to anything, you're observing. But how are you getting your sample is very important. So even though there is no regulation, my suggestion is you should regulate yourself in how you do things and do it properly. All right. I now want to maybe take a few minutes for some quick questions. I know I'm standing between you and the panel and lunch, but next topic is a statistical analysis plan. It's very short, so we can either do one thing, you ask questions now on sample size, or you let me do the next 6 or 8 slides, and then we have questions. You'd rather do that? Let's continue then. All right. So one thing is determining your sample size. That is done at the design stage, right? It's something that you're going to put in your protocol as part of your statistical considerations for that study, okay? You can calculate your sample size. Remember that there's all sorts of assumptions that go into the sample size. things that you're uncertain on. When I prepare a protocol that I'm going to submit to a grant, to a grant agency, I never say one thing only. When I have that sample size section, I give them a sample size sensitivity analysis. So I say, you know, if I have this effect and I have this much variability, I will have this much power with this much sample size. And I give them a table of different options. And then I say, I looked at all of these, and based on my literature review and my experience and this and that, I am choosing this one, as opposed to just giving one only. Because if you give one only, the reviewer doesn't know that you've done the other ones. And then sometimes they'll criticize you by saying, well, that doesn't seem reasonable. You didn't justify this. You have to justify. And remember that you are choosing one with all the uncertainties that went into the parameters of beta, delta, and alpha. Usually you keep at 0.05, but the sigma, the variability that you have. And so sometimes you're less certain about it, of what is the effect that I'm going to get if it's a new investigational drug versus something that has already been used for a while, a different chemotherapy or whatever, a new preparation. You have a lot of uncertainty. So it's always best to, when you present the sample size, you say, these are the options that I thought. And this, you present it in a table with different options and say, this is what I reasonably can do. I could do this. This would be best, but you know, this is going to be too expensive to get 2,000 people. Or it's not going to be practical. It's going to take forever for me to recruit 2,000 people. So I'm going to have to do it with this. This is the power that I can have. And this is the sample size that I can manage to get or afford to get for this grant. And remember that an underpowered study, or if you don't show significance, it doesn't mean that you did a wrong study. A poor study is one that, a bad study, a bad RCT, is one that was done poorly. A bad study is not one where you get a negative result. Keep that in mind. A bad study is one that is done poorly. Lack of significance doesn't mean that you did not provide quality information. So if you do a study well, you measure things appropriately, you randomize appropriately, you follow people appropriately, you get an effect size. You may get a wide confidence interval because you had underpowered, but that effect size is a valid result. And if it turns out to be non-significant, that's information. Somebody can take your study, done well, and put it with other studies that are done well and end up with a meta-analysis that now gives some conclusive evidence. So don't feel bad if your sample size, you cannot afford to do a big study, but be careful when you present it in your protocol. All right, statistical analysis plan. What is a statistical analysis plan? There are some guidelines that have been provided, and thanks to one of your colleagues, Vinita from Tata, I got these slides. So JAMA gives guidelines for the content of statistical analysis plans in clinical trials. And it's just a template for things and what should be included in it. So there's aspects that are administrative information, and you know, just things about the studies that are not necessarily more than just administrative protocol versions, etc. There's the background rationale for the study, the objectives of the study. And this is just very high level summary of what is the study about and the study design, the trial design, randomization, sample size, framework. In this suggestion by JAMA, they actually put the statistical interim analysis and stopping guidance as part of the statistical analysis plan. And I don't totally agree with that. I'll tell you how we do it in a second here. But they do in the timing of the final analysis and the timing of outcome assessments. Then you have the statistical principles of how you're going to do your inference, how you're going to interpret confidence intervals, how you're going to deal with adherence and protocol violations, which is your trial population, who is your intent to treat, who is your per protocol, how you're going to deal with withdrawals and follow-up. All of these things that we must at some point say how we're going to deal with it in our analysis. Then comes your analysis section, which is then very important. What drives everything is the outcome definitions and then the analysis methods. In a clinical trial, you usually have one primary hypothesis on the primary outcome. And so therefore, the statistical analysis plan would be just for that. However, many times you have secondary outcomes, secondary hypotheses and subgroups, and all of these other things. Those then become secondary sections of your analysis plan. So I like to separate out what we do for the primary analysis, primary question, and then all of the other stuff, secondary, comes later. And be careful in how you mention it, because if you are testing secondary hypotheses and and subgroups, etc., you must deal with multiplicity of testing and mention that. If you're exploring, then you're exploring. And if you're exploring, that's fine. Never mention the word significance. You say, oh, we found a substantial effect here. We found consistent effect in this group. We saw a big effect here. We saw a small effect here. We saw a great effect here. We saw an awesome effect here. But don't use a significant effect. Because when you use the word significance, it already implies you've done a statistical test. And if you've done a statistical test, you better have said, I've done multiple tests, and therefore I have to adjust for things. So be careful. If you explore, explore. There's nothing wrong with exploring, but don't use the term significance. So what we do is something a lot more simpler than that. We have a checklist of what should be the contents of a statistical analysis plan. So you don't have to go through the whole thing because you already have your protocol that has the design and the rationale and all of that kind of stuff. That's not part of the statistical analysis plan. Statistical analysis plan is how you deal with the data. How do you answer your question? So then you start by telling me what the hypotheses are. Start with your objectives. Which are the populations to be analyzed? What are the baseline characteristics you've measured? How are you dealing with compliance? How are you dealing with the follow-up and missed the follow-up and all this kind of stuff? And then go to the heart of the matter here, efficacy testing. That's what you're doing in a randomized controlled trial. So you give me your definitions of variables, and for every objective, you give me separately your analytic methods. The statistical analysis plan is not at all like that one little paragraph that people put in a manuscript that then the statistical analysis, they say, we use this software. For continuous variables, we use means, and for frequency variables, we use, for categorical variables, we use frequencies. That is totally not informative. That's like telling me, oh, in a chemistry paper, oh, for liquids, I use beakers, and to make things hot, I use a Bunsen burner. Well, who cares? That's what you would do anyway. For count variables or categorical variables, you do use frequencies. What else are you going to do? So why this doesn't belong anywhere? Say for this, I had to transform the data because it did not follow the distribution, and I therefore used this test, and I checked the assumptions of this test this way. You specify for each one. Luckily for a randomized controlled trial, we have one primary objective and one primary hypothesis. That's usually what you do. But then you do the analytic methods for each objective that you have, how you dealt with multiplicity, how you're going to deal with subgroups, and then you look at not only efficacy, you look at safety, again, give the definitions, what methods you're going to use, and any subgroup analysis for safety, and do the adherence to protocol. So what is key in the SAP is the primary outcome. That needs to be clearly and unambiguously defined. And it's very crucial to be unambiguous. Exactly how is it to be analyzed at the end of the study? You don't want a generic statement. It's exactly what you're going to do. It's measured at this time point. I'm going to take the difference between this time of onset to time of this, to that. I've got some example definitions. Sadhana gave you others that are used here at Tata. This I got from the National Cancer Institute as their definitions. You need to specify whatever definition you have, right? And sometimes these are defined the same thing, and sometimes you get criticized if you don't define it like somebody else wants it defined. So you need to just say, oh, we use disease-free survival. You need to say what disease-free survival definition did you use? What were the diseases? It's without any signs or symptoms of that cancer. What are the signs of symptoms of that cancer? Specify that. Otherwise, people don't know. Now, what is easy in a SAP is to say, for the primary hypothesis, the tests are going to be one of these easy tests. So that's easy. So the primary analysis, as I said before, is basic. What is complicated depends on if you have multiple objectives, if you have multiple primary outcomes, when you want to test in secondary outcomes, when you want to test in subgroups, when you want to test at multiple time points because you have correlated observations, when you have missing outcome data, how do you plan on dealing with it? And when you have to deal with residual confounding by regression because you did a small sample size and you didn't get balanced, you may have residual confounding. That's the part that's complicated in the SAP. The primary analysis under intent to treat ignores all of these issues. It's not a big deal. In observational studies, though, not much is controlled by design. So we don't have all that rigor that we have in the protocol of a RCT. So you end up, having to adjust an analysis. So the statistical analysis plan for an observational study is much more complicated than the statistical analysis plan for the randomized controlled trial. Only if you complicate things in the randomized controlled trials, you have it. If you just do the primary analysis, it's very basic. But usually you do all this other stuff. So in an observational study, you have all of those complications on the left, plus you always are modeling because you have to deal with potential confounding. Randomized controlled trials of large studies deal with the confounding by randomization and balancing out the known and unknown confounders between the two groups, okay? Now, as I said, there is no requirement for a SAP usually. There's no regulatory agency that tells you have to have a SAP for an observational study. But I suggest you do develop it. And many of you are doing observational studies. It's always best to have a SAP for it. In clinical trials, we do have a requirement for a SAP. In fact, you have to register not only your protocol, but you have to register your SAP. And if you have interim analysis and you have a data safety monitoring board, you have an additional consideration that you have to have, and that's called a DSMB charter. So a DSMB charter is a charter that goes to the members of the board that includes all sorts of things. This is the template that the National Institutes of Health have suggested of what should be the content of a DSMB charter. The responsibilities include a variety of things. They look at the efficacy, the benefit-risk ratio, how participants are selected, adherence to protocols, quality, integrity of the study, amendments to the protocol, performance, safety, and abnormal findings. All sorts of things they have to do. But you specify that in the charter, the organization, then all sorts of logistical things of scheduling, reports, etc. But then they also have statistical monitoring guidelines. And this is a second statistical analysis plan. So you have the SAP is a statistical analysis plan at the end of the study. But if in addition you have a data safety monitoring board, you have a statistical analysis plan for how you're going to do the interim analysis. And there's many ways of doing it. And we would take another lecture to go into that. But there are guidelines for early termination for benefit, or early termination for futility, or early termination for safety reasons. And that's part of that statistical analysis plan for the interim analysis, okay? That's for monitoring. So we'll stop there. Lots of stuff that have been presented, and I'm sure you have lots of questions. please. Thanks. Maybe everybody wants tea and don't want to. Yes, or lunch.
Statistical tool to help out, or we say we didn't?
So whenever you ask a question to a statistician, the answer you'll always guess it depends. So it depends. You can, if you can continue the study, because now it's possible that, let's say, technology hasn't changed, the situations hasn't changed, you did not spend the money that you were given, and you still have that money, so you can still do it. Prices have not changed. You are still interested in it. You have already been promoted to full professor, so you don't have to worry about delay or anything like that. You can still continue the study, right? However, it may be that those situations are there. If it's well conducted, now you could publish these results as saying, unfortunately, our funding ran out. We just cannot do it anymore. But we have done a study. We have an estimate of the effect of the intervention. We're going to have wide confidence intervals. You're completely transparent about it in the paper. You don't pretend like you've designed the study with 200 when you actually had designed it for 400, because you've already registered it. And the reviewers automatically, when you put in that code, they go automatically and look at it first and say, wait a second, you said you were going to do this, now you're doing that. So you have to be transparent and publish it. If it's an important result, whether it's significant or not, doesn't matter. And this is, I want to make it clear. People think that a bad clinical trial is because they did not show efficacy or they did not reject the null hypothesis. They didn't get significant. That is not true. A bad trial is one that was done poorly, not one that doesn't get significance. Non-significance is an important result. Yeah.
Well, thank you so for wonderful talk. So my first query is very simple, but I think I am the one who got confused. What is one-sided and two-sided alpha? Can you explain with an example how a clinician is going to decide whether he is going to use one-sided alpha or two-sided alpha to calculate sample size? That's the first question.
Yeah.
And secondly,
We need a whiteboard here.
and secondly, for example, you stated that TMS study retrospective penile cancer analysis. So they did it without sample size calculation. So can you give that example that how that could have been done in an idealistic way? How we could have calculated a sample size for that retrospective study?
So I'll answer the second one first. For that one, what they should have done is they said that first line should have been out. It's as in an observational study, if you have a hypothesis, if you are going to compare groups, you still need to calculate sample size. Now, the sample size in their case, if it's done retrospectively and they don't have the capability of having a large sample size, they just have the 91 that they have, well, then you use the formula a different way. You say, with the sample size of 91, I will have power to detect the difference of such and such, or I'm interested in being able to detect this difference, so this is how much power I will have. And so that you are, again, just like for him, be transparent in your statistical section and say, don't go by standard, most people copy paste and they just change the numbers. That doesn't make sense. Be particular to what your situation was, right? You said, we did this retrospectively. We had only 91. This was the way we had it. We are interested in this hypothesis. We will not be able to test it because we will have very wide confidence intervals. So therefore, we're not going to tell you what the power, we know we are underpowered, so we're not going to test it. However, we will present to you the Kaplan-Meier and discuss it descriptively, not mention the word significance, or we're going to provide you the confidence intervals for median overall survival, and it's going to be pretty wide. And we acknowledge that it's going to be pretty wide. That's all you have to say, and that will work. People think that they have to put p-values. People think that they have to put significance testing in every paper. That is not correct. Now, yes, there are editors that also think that way, and so it's hard to convince some editors, but that's why a well-written statistical analysis section and a well-written cover letter that goes with that, explaining this to the editor and being very transparent about it, does work. Editors do look at this. They don't ignore it. Oh, and your first question, one-sided versus two-sided. So going back to Dr. Mahesh's diagrams, I can't do it here because I don't have a whiteboard, but you have one here as your null hypothesis, and then you had your alternative hypothesis over there. And if you have one-sided, you're only looking at rejecting in one direction. But often, when you really don't know if something is going to work or not, you should be having a two-sided hypothesis, meaning that I will reject this if I observe that there is a difference of some kind between the new intervention and the control. And I could have the second one be here or the second one be here. And so I would have now that blue one here and one red here and another red here, but I don't know which one. And that's where the two-sided comes. Originally, people say, I don't know what's going to be, if this new intervention is going to be better or could be worse. And that's where the two-sided came. Now, we usually have a new intervention we think is going to be better. We assume it's going to be better. We're actually only interested in looking at it for superiority. So we're only looking in one direction. And we would then use, okay, I'll do it one-sided. But should I use the 0.05 one side? And again, the reason we do it two-sided, even though we are interested in a one-sided, is historical. In the past, people cheated. How did people cheat? In the past, I'm talking in the 1970s, 1980s, we don't have registration of clinical trials. We don't have we had paper protocols. There was no, digitized protocols that were around. And so what people would do is they would do the calculation and say, okay, we have to do it two-sided because we don't know if it's going to be better or not. And the two-sided at the 0.05 level is 0.025 on this side and 0.025 on that side. The critical value is 1.96 on one side and minus 1.96 on the other side. What would happen, in some cases it happened, is that you don't quite get to 1.96. You get maybe 1.8, get 1.7, or something close. And so the trick that people did is that, if I had done one-sided 0.05 instead of two-sided 0.05, the critical value would not have been 1.96. It would have been 1.645. Oh, now I'm statistically significant, and I can do it. Nobody knows. Oh, yeah, because we were always interested in that. So we didn't register any protocol, but no protocols were registered. And once they started having Word documents in the 1980s, still we're not registering. I can just change the date in my protocol and just say, oh yeah, this is what we had, and I can manipulate. And all they did was just exclusively to be able to claim significance when they were close, right? We had this situation happen with us in the studies of left ventricular dysfunction. It was started in 1986. It was ending in 1991. It was designed as a one-sided 0.05. It was designed like that. So we had protocols written, but they were not registered. When we sent it to the New England Journal in 1992, the statistical editor there said, no, you have to do it one-sided 0.025 because that's two-sided 0.05. And I was a junior statistician, so the head statistician was writing letters back and forth. We designed it this way. We, because it would not have been significant. It was 1.8 something. And we designed it this way. We have this protocol. We are not cheating. We have always done it. The editors insisted, no, we don't want it that way. So we as statisticians told the investigators, well, let's not publish in New England Journal. Let's go to another journal. All the investigators said, oh, we have to publish in the New England Journal. So we compromised. We talked to the editor, and the editor allowed us to do two things. One is we had to do it one-sided, two-sided, reported two-sided, but he allowed us to put a little footnote at the bottom saying the adjustment to doing it one-sided, two-sided was because the editors of the journal requested us to do it, something like that. But, these things happen. But now it's standard that to say, if you want to do it one-sided, do it one-sided at the 0.025 level, which is equivalent to doing a two-sided 0.05.
I'm sure there will be many more questions, but in the interest of time, I think we have to stop the Q&A here. But of course, Dr. Bangdiwala will be here with us till tomorrow afternoon. So I think you should definitely kind of meet him and ask him in person if you have any further questions. Okay, and so now we have to move to the next item on the agenda, which is a panel discussion to discuss the challenges faced by young researchers, oncology researchers, in conducting clinical trials or clinical research, and for which I have my good friend Dr. Jayant Goda, who is a radiation oncologist at Tata Memorial Center, as the moderator, and he is going to introduce the panelists, and we are going to have a short panel discussion on this. And this is going to be a very important discussion for all of you, because they're going to touch upon all the important elements that may be challenging, for a budding oncologist, but through the wisdom of experience, they're able to kind of sort it out for you and how to find solutions for those problems.
Okay, good afternoon, and thank you very much, Vikram, for introducing me. And I'm not going to go beyond the time. We are short of time, but definitely we should be able to finish it by 2 o'clock. So, what I'm going to moderate is about meeting the challenges in oncology research, and which we should all know it from the experts. And here I have very well-known panelists. Dr. Srikanth is anyways here. He's from McMaster University. So can you just come over here so that you can sit? And he's a biostatistician, and you've heard his talk. Dr. Bharat Rekhi is my friend from Tata Memorial Center. He's a pathologist and is actually a prolific writer as well. Dennis from St. John's Hospital. He's a clinical pharmacologist and has got lots and lots of experience in conducting clinical trials, especially heart-related cardiac trials. Shwetab, my junior colleague, is a radiation oncologist from Tata Memorial Center. Please, Shwetab, come here. And Balu is there, Dr. Balu Nair, radiation oncologist from CMC Vellore. Shwetab, yeah. So, what I why don't you come here, Balu? Come. So what I want all the panelists is that let this be an informal session. Please don't stop yourself. Don't give diplomatic answers. Please open your heart. Please answer with your heart, not with your mind, right? Because that's very important. We do face challenges, right? All right. So we as clinical researchers, at least from LMICs, do have some inertia in writing for clinical trials, implementing those clinical trials. I think it is true. What do you people think? Just raise your hands. Is it true that we have inertia in writing and implementing, doing clinical research in our setup? So I could see so many of them, right? So it is true. And what do you people think about it? Is it true, Professor Bangdiwala?
Well, I'm not sure it is true. It depends, right? So what the inertia may be caused by lack of funding is one, lack of resources, or also the extremely high demand for clinical involvement and seeing patients, etc. So it is a more of a
How is
practical
it-
thing.
How is it in the Western countries? I mean,
So again, it varies there. In the United States, it's very different from Canada, for example. In academic settings in the United States, it is the one way people progress in the ranks academically
yeah.
is to have grants, to do research, etc. And even though you're supposed to, there's three things that judge your career, which is teaching, service, and research. Research is weighted a lot more because research brings in money to the universities. And so there is a stimulus for it.
Incentive to
The
do this.
incentive is very high because the promotion groups will be heavily affected by how much money you brought in as opposed to how well you taught in classes, etc. In Canada, it's different because in Canada, where I am now, when you submit a grant, you cannot fund yourself, but you can fund staff, and you do get lower overheads, so smaller amount of money coming to university, but still is pretty much driven by research. So I think it's not the inertia. I think it is how the research is stimulated by the money aspect of it.
That's a completely different thought process that we see in the West. Can I ask Dr. Shweta, my colleague here, do you think it's true that there is inertia in our setup? Yes or no? It's as simple as that.
So I'd like to answer this question in actually two parts. So where we are working actually, I think in an institute like Tata or let's say some other tertiary cancer institute in India like AIMS or CNC Vellore, I think most of us are too much burdened with our clinical work also. I think that is one of the things that when you start as a junior faculty, I think everybody expects you to do your clinics and focus on your clinics much more. First 1 or 2 years, you are actually advised to do your clinics, and research can always happen at a later time. I think that is not necessarily such a bad thing. I think you actually get to know what questions are worth answering when you do those clinics independently. In residency, it's a completely different, your thought process is completely different. Once you are an independent consultant, you get to realize what questions need answering. Sometimes it can be overwhelming. I think we all go through a phase where every single day you will have one new RCT in your mind that why is this question not answered and why people have not done an RCT till date for now. I think that is where a senior mentorship really plays a big role. Go back, speak to your unit head, your head of the department, who's a senior in your department, that okay, this is a question which is vague, which is a gray area, but still why people have not done trials, and you will get to know that there are hindrances. Either there is a problem with the accrual or the design, or people have tried it and failed. So I think that is where one of the bottlenecks is when you consider about early career research. And the second thing is actually the financial aspect. I think most of us, including me, when I started, I've been a faculty now for 3 years. I was absolutely unaware of how to get grants and get even intramural funding for a trial that I'm thinking of designing. What are the headings? What is the proper way of writing a grant? And I think we are blessed that to have a statistical backup. We are blessed to have experience from other clinical researchers. But financial aspect is something which is a big deterrent when we you are saying, sir, that are we lacking in having that intent to do a clinical research?
Dr. Bandiwala gives us says that doing research is a stimulus in Western countries, but here there is some inertia because of certain reasons. What Dr. Shweta has put. Yes, so there are challenges, and there have to be some solution to those challenges. So what I'm trying to do is that I'm basically breaking them into these challenges, and we try to find out the solutions to this. So I'm going to ask questions on research environment and infrastructure, ethical issues, governance and regulatory issues, competing demands of working in a high throughput center, just as Dr. Shweta has told, then how we can actually have solutions to that, human capacity, human factors, financial and operational barriers, and ultimately last ones, the others. If we have some time, I'm going to talk about that. So let us know it from our experts now. Let's start with the research environment and the infrastructure. Dr. Bharat Rekhi, would you like to comment on this, especially in LMIC? We know that the research environment and the infrastructure is very good in Western countries. I've basically trained in Canada, in Princess Margaret Hospital. The infrastructure is very good. The environment is very good. How do you think it is here in the LMICs, keeping India as a model?
I foremost have to thank you, and I'll take cues when you said that, speak from the heart, your experiences,
Absolutely,
and
we should
such
speak from the heart.
valued points, which I have just heard. I think we always talk about the barriers in terms of financial, thing. LMICs have a great data to showcase, but funding, we always talk about. But I'll take it to something very basic, trying to create an environment or a value system which celebrates and which I think empowers research environment right from the younger colleagues. Because as a pathologist, and it's an investigative branch that I work in, there's a perception in some ways, that there's a service versus research. I think if we realize quite early that service is with research, and in academic centers, blessed to be working in centers like this, if we feel that we are engaged in research in any ways, retrospective, prospective, our cities and clinical sites, we can bring more to the service part. So I think that thought process has to be right ingrained, and then you take it further as the mentors and the higher authorities empower those individuals and accordingly identify people who can take it both versus who would like to take further only service. So I believe it's not a versus situation, it's with, and I think that's how we can sort of create this value system and take it further.
So you want to say that you want to segregate individuals who really want to do service and who really want to do research, basically not penalizing those individuals who don't want to do research.
Yeah, so my first point, like I said, is to have a value-based system of knowing that research is integrated as part of service, especially centers like this, because you can bring more. We're talking about evidence-based and precision-based medicine. That's research is so integral part of it. So it's not a versus. The first point is to know that research brings more to service. I think that is one point.
I think that point, that message needs to be
Very much ingrained, and I would be very pleased to see if my more pathology colleagues and residents were also showing up here, and all the clinical colleagues, to know that and to discuss this. And the second point that you said, because individuals have their different abilities, so we cannot judge everybody with the same way. So somebody might be very good at patient interactions and doing clinical, somebody might like to do both, and somebody is purely towards investigation, not judging but seeing their contributions. I think we can identify that way and have individuals accordingly sort of when you look at their promotions and judged in that way. So I think that's
two different yardsticks for
yes.
That's a very good thing actually, and maybe that will also incentivize people to do
Absolutely.
research also.
Absolutely.
Both are equally important.
Absolutely.
What I like what Dr. Shweta told is that in the initial years, you should be doing more of clinical work, because when you observe seeing your patient, then ideas actually come to you. So I think this actually can be taken forward, both are integrated, clinical service as well as research. So it's one of the important things in research environment is to integrate both clinical service as well as. Now, the second important thing in the research environment, I want to ask both Dr. Dennis as well as Babu. Do you think that students at the undergraduate level, from the MBBS level, should be trained in research so that when they move on to postgraduate level and in the early years of their career as a clinical researcher, they will already have developed that inkling towards both Babu and Dennis? What are your thought processes?
Okay, thank you. Very pertinent question, and I'll be happy to answer this. So, firstly, research is not for everybody. And in the extremely busy and stressful undergraduate days, again, forcing research on them is not correct. Postgraduates have to do research because they have to learn about research. So you do your dissertation, and most people don't want to go back and visit that dissertation they did for whatever reasons.
Yeah. Okay.
We'll not talk about it. Okay, now
that's the fact.
and okay, so the second thing is okay, very quickly, let me tell you, since 2009, I got a grant from the NIH. A part of that grant was for building capacity. And since then, we've been running undergraduate research mentorship program. At the time, we had 60 students, so only 10 were selected. Right? And then we worked with them for 9 to 12 months, matched them with a mentor, gave them some money. They did that. So only 10 out of that many students. So for a few years in between and COVID, etc., we had an interruption. We've restarted it and we're continuing. So 78 projects have been completed as part of this program. And again, it's not for everybody. And critical for undergraduate students is to find the right mentor as well. And unfortunately, like every other skill, mentorship is a very advanced and fine skill. You may be a good clinician, a good teacher, a good human being as well. Doesn't make you a mentor, right? So if we have to build research in India, we actually have to build mentors in India.
Has to be from the classroom level.
Yes, yes. And again, mentorship also is not for everybody. You must love to mentor people. When your mentee walks in, you must feel, good. Here is an opportunity for me to grow along with the mentee, not to say, oh, this fellow has come again. He never completes his work on time. Okay, anyway, sit. You have problems and you're dumping your problems on me. I have my own problems. It's a mindset. So mentorship is not. So I think this is critical. And again, even for faculty, while I broadly agree with everything that was being said so far, even as faculty, research is not for everybody. And sir mentioned very nicely, you may be a very good clinician, you may be a very good teacher, you may be very good interacting with patients, you may be a very good administrator. Okay, but there are only very few people who become clinician scientists. So you're able to straddle both clinical medicine along with research and publication and interaction and all that. So we need to provide the milieu, the environment, and that's the job of senior people, of institutions, and whoever the powers may be to create that.
We don't have senior people. I'm thinking they should have it.
Yeah. No, absolutely. And that's important. In fact, the last few years, particularly after COVID, I've been giving this lecture on how to build a culture of research in institutions. I'm happy to share those slides or do it online anytime. And these are the two things. So I want to stop this discussion with telling you people, when it comes to research and high quality research, we need to keep 2 F words in mind. Shall I say that?
Sure. No. You have to come out with your heart, not with your brains.
One is you must do research with friends and you must have fun doing research. And when you enjoy research, you want to do more and more of it and do it with friends. No high quality research came just by one, brilliant genius somewhere sitting in the corner. And one of my friends, PJ, used to say, he still says it, okay? He says, the good thing about research is you don't have to be a genius. You just need to have a little bit of different important things, put it together, but persevere. And one more thing is, for research, you need to have the passion. 2 P's now. Okay, one is the passion to make a difference to your patients. Publications, prosperity will come later. The other P's will come later. So passion for your patients. Can I do something for this patient? Then after that, you don't have to work hard. I was just telling Jayant a few moments ago, I will continue working because we just enjoy work for the sake of working. And then you choose what you want to do. So in summary, everybody needs to know about research, but everybody should not have to do high quality research. Don't push them. Then you'll get horrible research, you'll get fraud as well. That's something that I caution people. You push people. And again, Dr. Bangdiwala said it beautifully. And I say this also, negative result aa gaya. This is horrible. The study failed. No, it is whether you got a clear answer or not. Did your intervention work? You have a clear answer? Yes. Your intervention did not work. Is that clear? Are you sure your intervention did not work? So I personally don't like to call it a negative trial. Is a good quality trial or a poor quality trial? Right? You got a clear result or not a clear result? And this is the attitude with which we need to go ahead and do research for the patient, with the right purpose and the right passion. Another P. So F words and P words. That's what I spoke about. From my heart, you asked.
When I used to attend some workshops, the senior hemato-oncologist, Dr. Walker deemed actually to do research with like-minded. So then it becomes fruitful. Yeah, then it becomes fruitful actually. And we also do research with recreation, R&R. Yeah, that is the buzzword that you have to think about. R&R, research with recreation. It should be fun also. Dr. Balu, what are your thoughts about this?
No, your question about whether undergraduates should do research or should be taught research.
They should be trained, whether they should be trained from that grassroots
Okay,
level.
so I would say undergraduates should be trained to ask questions, which absolutely doesn't exist in India, because we actually are taught to listen to seniors and then read from textbook and think that is the truth. We are not asking questions. And I see that when you come as postgraduates, first stumbling block is the right question, that nobody raises questions. And we have to, as guides and mentors, we have to bring questions into your mind. But if we train the undergraduates to ask questions, obviously that first block is
So
gone.
no question is a stupid question, basically.
I mean, how many are raising hands and asking questions? It's not in our culture, and we need to change that. And the research has to be taught at postgraduate level. So once you have the questions ready, you can train them to do the research. And when you speak about inertia, I don't think the environment is the inertia. Inertia is within. So inertia is, by definition, is the first resistance for an object to start moving. Okay, and that is within yourself. And if you all have come here to attend this course, you are all planning to become clinician scientists. And I don't see that you are, so that first block is gone. No, the first research that you do will keep you moving. And that's why you are here. And so that's why the first research that you design should not be an undeliverable triple-blinded RCT. It should be something which will help you start moving.
Thank you. How is it in the Western countries, especially in America and Canada?
So you're talking about undergraduate
Right from
training.
that, yeah.
So unfortunately, they don't teach how to do research at the undergraduate medical one. And I don't think they should be forced to do research. They should be taught the knowledge of whatever science aspect they're looking at through research. So they need to be taught the value of research, as opposed to be sold, this is the way it is, as opposed to this is the current understanding of the way it is based on current research. So they see the value of research, they understand the value of research, and because research means that we don't know the exact truth. And if everything is communicated as this is the exact truth, that means that there is no value for research. So my position, and again, speaking from the heart, is that undergraduate medical students should be taught that whatever science discipline they're studying at that moment through what is known by research at that moment in that field.
Nice thoughts, basically. This is, I mean, we are able to get something about the environment now. Let's get into the infrastructure, right? What are I know that when I was doing my fellowship in Princess Margaret Hospital, the infrastructure in PMS was absolutely very good. Whatever I wanted, whatever journal I wanted, I just had to mail the library. I used to get that soft copies of it, whatever I wanted, and the materials, whatever I wanted, used to get it within 24 hours. Now, Dr. Bharat Rekhi and Dr. Shweta, what are the challenges that an institution, again, you can basically, we have got academic institutes, we have got state government institutes. So I know the difference. Now, can you just enumerate and highlight some of the differences as far as research in these higher academic and state?
So foremost, I don't want to sound complaining at all. You know, that's what I want to begin.
Yeah, you can take this.
So see, I think if you want to pursue research, which I think with your choice, with your thought process and the influence that you've had, and you've chosen to do so, so one has to take an initiative. And I won't say versus higher academic centers versus, of course, there are funding is more accessible, believed to be in certain centers versus not the others. But I think there are a lot of agencies which, if one is interested, can explore and should explore, but you have to come, it has to come from your what shall I say, drive. That has to be the personal drive to pursue research with like-minded people, which you might be able to choose or not, but you have to figure out a way to do so, and then you accordingly look for the funding opportunities which are required for your research. So I think one needs to pursue this. And if you look at the differences in, so there are funding opportunities even for the not so higher institutions, because ICMR and other DBT. So people need to be knowing how to formulate a good study. If there are a lot of investigators might not be aware of workshops like this to know about sample size designing. It's a fantastic talk, something very crucial, and that takes away their opportunity to get, even if they apply. So I think more awareness about designing, formulating studies, and I think there are opportunities, but it has to be there has to be a drive within the environment that you have, with the choices that you can make, and I think it is doable. So I worked at different levels. I can just share my experience as a researcher. So I didn't do demonstratorship in pathology, but that gave me a chance to work in tumor biology lab, and I was seeing that as a pathologist, when you collaborate with people that's what first editorial I wrote for my journal also. Collaboration is the key. That you collaborate with people, basic scientists, clinical colleagues, and pathology is like a bridge. We form together. So and then you formulate research, look for funding, have thought processes, and be aware of certain workshops to be able to design a good study. So I think it's doable, but of course there can be a perception of different opportunities at different institution level. But I think it has to be self-drive.
So do you think that different institutions have maybe there are deterrent sometimes to basically inculcate the habit of research
So
in
that's
their
yes. So that's what I said initially. The value system and the atmosphere, and which our esteemed colleagues have said, and that's what we learn from the West. How it's not only that you bring monetary aspects through research, but I think the final point with that research is also what you bring to clinical service, and that's how you get to know about the newer drugs. The how they are working, newer tests, what is working. For more precise diagnosis. I think that level of, and sometimes.
you mean to say there should be some amount of research autonomy?
At the community level, people, now we know trials which include patients, patients are involved actively in those trials. So even at the community level, if there is an advocacy about research and people get to, that's how it can come.
Yeah, I'll come to that later. So you have already talked about it. I've got that in this slide. But good that you have spoken about it. Now, Dr. Shweta, can you just give some solutions as to how any infrastructure, like for example, you're working in some hospital, how that hospital can help you to promote research or doing your research or implementing your research protocol?
So I think when most of us join an institute, I will actually briefly mention when we talked about that not everybody can be a researcher, and I think that is absolutely correct. But what is made to feel to most of us when we join an institute, particularly a tertiary cancer care institute, is that research gives you fame. Research gives you a good starting point in your career. Research makes you famous. Research makes you popular. Service probably, because research is probably more quantifiable than, let's say, service, and people don't value service as much. That is not absolutely correct, but that is the feeling that is given to many of us when we join the institute. From my personal experience, what I could gather was that most of us want to do, when we join first year, second year, we want our first research to be a 600 patient phase 3 randomized control trial. It doesn't necessarily have to be that. It can easily be a retrospective observational study that you do, design your hypothesis. If there is a question that is bothering you in your clinics, just go back, look at the data, try to clean it up, try to analyze it with the help of your statistician, and that will give you enough answers as well as help you design your future study in a much more pragmatic way. Your first research does not have to be a phase 3 randomized control trial involving 1000 patients, and you are applying for funding here and there and nobody is helping you out, and then you are saying that junior researchers are not being promoted. So I think we also have to look at from, particularly as Jayan sir said, from our perspective and our LMIC perspective, that we have to think more pragmatic, and as and where we go along, we have to adapt to the existing situations. If there is a funding opportunity where some senior actually is willing to help you in writing your first grant, I think we all should grab it with both our hands. I think it is easier said than done in a tertiary cancer care institute like us as compared to state medical colleges. I have been undergraduate from a state medical college, so I can tell you, but I think situation is gradually increasing. There are certain startups which are actually helping people do a proper statistical analysis even when there is no formal help available in the institute. I think they have a long way to go in promoting the culture of research in small medical colleges, both government and private. But as of now, my practical advice is that don't start big. First start small, look what you are doing, and then take it ahead.
So bottom line is that we should have a very conducive research environment to do research. And also wherever you're working, they should be encouraging to do research. Either they can help you monetarily or at least in a psychological way, that they should help you to, I mean, they should not be a deterrent to do any research. I mean, they should not put that burden on you to do mostly clinical services and not do research. I mean, they should allow you to do research as well as clinical services, both the things. Okay, like the next one is also very important, Bagniwala. It's about the challenges that we face at the ethical level, at the governance level, and at the regulatory level while developing a protocol and while implementing it. What are your thoughts about it?
Just one, I want to go back just a little bit to the infrastructure. And one thing is also to realize that research is among friends, but it's also among different disciplines. And so part of the infrastructure is also having adequate data management support, data quality support, statistical support, having computer support, having all of these things. Does an institution provide it? Institutions like Tata, you have it, but not everybody has it at their institution. And it's necessary for good quality research.
So you think that institutions which have got very little support, they should also find support for the smaller institute?
Yeah, so that's one way. Now, your question now is on ethical governance. So again, this depends on the whatever structure you've got in your institution, as well as your country. And so I can just give you an example of Canada, how regulatory bureaucracy in Canada was such a huge stumbling block. COVID came, to being able to do quick quality research. Had to go through the same bureaucratic process, having the institutional review board, having the provincial review board, having the federal review board of Health Canada decide whether your study would be approved or not. By the time we did that early on, when everything that was being tried, like from stupid ivermectin to hydroxychloroquine to azithromycin, whatever, we would propose something. By the time this happened, already what we had proposed had been discounted by another study. And when we tried to use it as a platform trial, now we were said, well, wait, no, you have to submit again. Another 6 months to wait. So bureaucracy and regulatory is a horrible thing because it assumes that you're not doing things ethically. That's why they want to regulate.
Needs to be a change in
There needs to be a change in mentality and in certain situations. It is a necessary thing. Be monitored, regulated, look at it from an ethical standpoint, because there are people that are unethical. But there are circumstances that you need to sort of be flexible on, and that was not there. I don't know the situation exactly in India on that front. Let somebody else do that.
Same thing with you.
We always say regulation is bad, and why do we have police? Because we have crime, isn't it? So we should look at how many bad studies the regulators have weeded out and saved the people from. So there is a need for regulation, and being aware of the steps of how to approach it is very important. And that's why networking, collaboration is important, because people will share know-how. There is a lot of regulation in India at various levels for collaboration and all. So if you know that, you will know what is that you have to do right to go through those gates. And that's the way forward.
Dr. Dennis has to leave, but I would ask for his also opinion, then you can leave it.
Yes.
He has got a flight to catch. Then
Yeah.
we'll discuss amongst us.
So let me give you lots of good news about doing research in India right now. Okay. So firstly, I hope all of you are aware of the new NDCT, that is the new clinical trials and regulations 2019. In that, they've clearly defined what an academic trial is. You don't have to go to the regulator for that. Okay. So there are requirements for that. If you want, I can send you the slides. I've given this talk multiple times. Number one. Number two is, okay, let me come to ethics. So during COVID, we did kind of like a follow-up study for those taking hydroxychloroquine. There was no data. I mean, Trump was trumpeting there and whatever else was happening here. Okay, so we said let's follow up. Okay, believe it or not, I presented this to the ethics committee at 10:30 in the morning. I got queries by 5:30 in the evening. We replied by 7:30 in the evening. Next day morning, approval. This is the ICMR's. We had a group in Bangalore, the ICMR Bangalore. They did it for us, and we did simple data collection. In a matter of 2 months, we collected 12,000 patient data. Okay, eventually the treatment did not work. It's a cohort study. I mean, I go around preaching you can't use a cohort study to say whether it works or not. But 12,000 people, and these were people in the hospital who took this. So I wanted to give you that example that it is possible. There are good people in India. There are good systems in India. We need to go and find them. Okay, that's number one. Now comes to funding. Yes, about 8-10 years ago, it was very, very difficult to get funding. Since 5 years, things have changed dramatically. Initially, starting with DBT and BIRAC, they're giving 20-15 crore grants just like that. I'm on multiple committees. I remember one day we sat and actually approved grants worth about 60 to 70 crores. Of course, preliminary work, whatever happened. Okay, so ICMR now has got lots of good schemes where fewer people are getting significant funding. Previously, it was small funding for many people. They said we'll keep everybody happy, and nothing came out. The people did not even complete the project, leave alone publishing it. Now, giving few. So therefore, okay, so it's a good news for funding as well. The last thing I will speak about is ethics. Yes, a very good point made about why we need regulations, both at the regulator, even at ethics, because there are bad apples out there. We need to weed them out, and hopefully this will bring in good quality studies. But at the same time, we have to get trained on how to deal with regulation. Okay, you can't go untrained into any area for that matter. I mean, to drive a car, you need training. So before you get on the road, you get trained. So before you approach regulatory ethics, you need the right training and also the right mindset on how to work with them. Again, I'll share these slides with you. I have 2 slides on how to work with an ethics committee and what upsets an ethics committee. Right? So your research question, your statistics, your sample size, power, everything may be good. But there are certain things that irks ethics committees. You rub them on the wrong side, I mean, they'll get upset. Some of you will be on ethics committees soon. So these are things to keep in mind. So bottom line, it's a good time to be doing research in India. There are good regulations. There is funding. Ethics are largely, I mean, the ICMR document, if you have not seen it, the 2017 document, please download that and see it. A very, very nicely written document on Indian GCP. So lots of people also getting trained. So it's a good time to be doing research in India, and you people are super fortunate to be part of this excellent course. And with that, let me also say my goodbyes to everybody.
Don't leave without taking it.
Okay, we'll do that. Okay, so thank you all for this opportunity. I will, when I'm coming down, I'll say, yeah, we can continue.
Just wanted to say one small comment on the ethics. I completely agree. We need to have ethics boards because there are bad apples out there. But one of the things that when we do, for example, multi-center studies, we have to get approval from the ethics boards of every center. If there is one center that makes a little change and suggests a change, one ethics board makes a change, now we have to get it back on the other. What is happening in multi-center studies that make it complicated is that one ethics board does not trust the other ethics board. We need to figure out a way where an ethics board from one institution will say, yes, it was approved by the ethics board of this other institution. We will abide by that. We need to have something like
So
let me-
that we should have a harmonization between all the ethics boards, different. One is enough for all the others.
Let me give you good news even for Canada. Likely you're not even sure, Shrikant, which is, as part of the ACT grant, EJ. Yeah. So I'm on the International Advisory Board. So I was there, a few weeks ago in Vancouver, where a group of Canadians got together to get this. It's almost done. It's almost done. So Canada will have a central ethics board. And in India, I was also part of a committee a few years ago, though. It's not common, but people are talking about it. Documents are written. So we will have at least scientific review centrally. Only local issues. So ethics committee shouldn't be, looking at again sample size and power and eligibility. Look at local ethics. And quickly and timely manner. With that, let me run. Thank you all. Wonderful. I'm not able to be here this afternoon. I meant to be here, but some family issues I'll have to leave. All is well. It's my daughter's birthday. Today morning I woke up and said, no, I want to be here. That's my only thing. So it's going to be hard. My head said be here. My heart says to go. So I'm going. So
Okay,
I'm
all
going.
right. But
Thank
you
you all
take
and
your
bye-bye.
lunch but you're going to continue. You're still going to continue. You're not going to see you later. So I'm going to ask another question, both to my colleague who is from TMH and Babu who is from CM. Great, we should have an ethics committee. Sometimes when my trials don't get cleared and they take a long time, I think that they are the worst enemies of all. How much correct is that? I mean, that means they have got a lot of autonomy. Ethics committee has got a lot of autonomy. But sometimes in my heart, I feel that they misuse. How correct am I or how wrong? Dr. Shweta from TMH and Dr. Balu from TMC. Both are from two different institutes. Both are members of the ethics committee.
Yeah. So, first and foremost,
I get frustrated sometimes.
no, even ethics gets frustrated. No, so I'm in the ethics committee for the last 4 years. So the biggest frustration that the ethics committee has is when the researcher thinks that the question is already answered. Their entire write-up is such that okay, I found the answer for this disease. So when you write a research, you are bringing a question which is unanswered, which can either go negative or positive. You should have that thing presented to the ethics, but you come with a question and say that, okay, this will work fine. There will not be any problems. But the ethics can see the problem side of it. So it is actually nudging you to think, see, there could be another possibility. That's why you're doing the research. So that's where most times ethics get in trouble with the, or you get in trouble with ethics. Yes, it takes time for ethics committee to, that depends on the local, this thing and the how quickly you are returning. Most often, when people answer questions in a, at least 80% satisfactorily, we kind of approve the results as long as it is not going to be harmful to the patient. So I feel it is a good exercise because ethics also will see how when this data goes outside, you are going to get more questions, and that questions are asked upfront before the trial is even started. So that's how I see it. Maybe the turnaround time, that is an internal issue and that should be worked on. That's what I would say.
Before that, Shweta, you're a part of the ethics committee member. Sometimes I do feel that the power which has been given to the ethics committee, they sometimes misuse it. Please prove me wrong.
Before that, the power given to you as a researcher, you may misuse that. So that's what the ethics is trying to prevent.
I would appreciate if you would prove it wrong. That is the message that we send to the audience, that ethics committees are not meant for misusing them. meant to actually help you.
What, can you define the misuse of power of ethics
I
committee?
don't want it.
No, see, rejecting a proposal is not misuse of power. That's a conflict of interest that you have to address internally. That should not be a generalization for an ethics committee. Okay, that's a conflict of interest. Usually, when such a thing comes in our ethics committee, the ethics member will either stay outside or go and sit with the researcher and then present. So that's the general functioning of an ethics committee. So that's an internal issue which but that doesn't mean that the ethics is bad. So I would like to ask you, what exactly is the problem? Is people asking you questions regarding your research and write-up, is that a problem? You want to attract that question so that you want your research to be better. Okay, so you are putting it for review and you need a critical review. Why do you want an ethics committee who is saying, everything is good, go ahead? That's not what you want. You want them to thoroughly check it and find flaws with your protocol. That's why ethics is sitting there. And you see it as a positive step. The time taken has to be less, I agree. That also has to be sorted out.
So
I'm
walking-
being the devil's
yeah,
advocate,
I'm
but
walking.
you prove me wrong.
I'm walking on thin ice here because
No, everything
I
has to
think
come
sir
from
can
the
go
top.
back and tell to.
No, everything has to come from the top.
Yeah, so I will tell you where I think the ethics committee can improve. Right now, we have a committee which sits once in a month, and every in an average ethics committee, I think we go through 30-35 protocols in one or probably 6-hour, 8-hour session. They're a mixed bag. I think 3 or 4 prospective trials, out of them 1 or 2 big RCTs. Then there are certain single arm retrospective analysis, some animal, if you're in ACTREC, there are some certain animal studies also which sometimes come. I think where the researcher gets frustrated is the turnaround time. And I think what we can do better is that if there is a certain doubt which we feel that can be clarified then and there, the researcher can be immediately asked to clarify it, and then we do not wait for the full ethics committee to go back, sit down again and see, this is his answer, probably okay, then what about this thing? Then again that query goes back, then again it comes back, and that is where most of our researchers feel frustrated. I see 2 ways around it. One is again there are its own ethical dilemmas with it, that probably not in the first meeting, but in the second meeting, the researcher or the PI should be allowed to explain his or her point of view. The second is the off-meeting communication. The researcher should be allowed to explain his or her point of view to 3 or 4 members of the ethical committee on, let's say, on an email or in another short meeting, where these issues can be sorted out rather than going on and on again for 5-6 months and small queries coming back again and again. I think that is where most researchers lose hope, and probably that is the point that people are making, that if you are in the ethics committee, your research is getting approved much more quickly because you are able to explain your points much more quickly. And
Does that happen in your?
No, it's a very good idea. It's a great idea to have it with interaction at that moment, or maybe not at the moment because you have such a volume of things to deal with in one day, but that there should be a rapid screening with queries that are answered. We say we're going to meet again here. This is not whether it's approved or disapproved. It is queries that you can address. So then we streamline the process of review. I think that's one thing that needs to happen.
Yeah, I think it's a process issue rather than a philosophical issue, that you should get your systems right. And I understand that our turnaround time is around 2 to 3 months to get all the papers ready. That's because on the day of submission itself, people will not be fully done with all their paperwork. And then they will take another 3-4 days extra. And finally, when the ethics say, so what the solution CMC has found is to have electronic submission now, electronic review. And we are also looking at anonymous review system.
If there is an interaction with the researcher, the initial.
Okay, so that again brings the question of then again the question of bias comes in, and there has been instances where a cardiologist have called me and then been angry with me. Yeah, so why can't it be anonymous now? See, even do journal publications, we do get anonymous review and we are not angry with them. We are frustrated, but we can't identify an individual across it to whom we can actually ascribe conflict or things. So that is a way, probably in large centers like this, you should have anonymous reviews. That's the way forward. I think I'm for it. Electronic, no?
You can do it electronically.
Electronically. It's electronic. Yeah.
Also, it takes.
So again, that's a process issue.
Yeah. So the bottom line.
So one line in CMC is, if the researcher has responded and the reviewer has not responded back in 15 days, it is turned as a acceptance. Okay, that is a clause written in our submission. The reviewer, the onus on the reviewer to actually respond within 15 days, because there are multiple reviewers. So if one doesn't respond, the other response is taken and gone.
That fail-safe mechanism you're calling it. Maybe that's a very good idea. So the bottom line is, from this previous testing and from this interaction, is that ethics committee is not an enemy of ours. They are there to help us out, and they don't misuse their powers. Am I right? Do everybody agree with that? Yeah. Okay, right. The next one is, many of you have already discussed about it, is the competing demands of working in high throughput hospitals and academic districts. Bharat, you're a pathologist. I know how busy you are in your department, crossing, seeing the microscopic slides and all those things. So this is a challenge, I also know. But how important is the solution?
Yeah, so you have challenges, and I always say there are opportunities at the same time. You know that we need to be aware, and we are. So we do work at a very super high throughput center with a phenomenal number of cases that we handle. You know, as pathologists and you as oncologists, clinical colleagues, and all everybody. So I think it's important that again with the tuning to your mindset, knowing about how you can do, working out, discussing. And I'll just, if you permit me saying just before, because that discussion, I think a good quality research will be scientifically very sound. So I think, and I see it at different levels as an editor of a journal, as an investigator. I was also in the ethics. I'm glad you didn't put me in the spotlight, but just, I know. But, I think we do really feel, but it just improves. You answer and the queries from the ethics, and it improves your level of your level of final outcome of the research. With that mindset, I think with that, yeah, and then you don't have to answer. And now if you look at the impact factors of journals influencing, requires the ethical disclaimers in studies. So it's very, very important that it's sorted out quite early in place, in institutions, and then we can take it further. Now, what was your question? I was just
competing demands of the working in a
yes. So how do we balance towards our pursuit of and it's very Herculean with the three mandates of our hospital that we have: service, teaching, and research to but we look at it in a perspective that how they are integrated, and what we can. So you can't have when we score it, sometimes you feel tempted ki I did everything so much, but the total bit should be more or less, and then your perspective. So I think we need to know that how things come together, your research, people who are interested. Like I agree that you can't thrust on everybody to do research, but see their abilities towards what they have contributed in whatever ways. And similarly, teaching is a part of your service. How I always tell residents, if you are teaching, you are learning also that way. You are refreshing your basics in place. So it's all integrated, but we have to balance with the the time, and that's a bit of a challenge. It's indeed a Herculean task for us, but I think it's also a responsibility for us as big centers to be able to bring out. Otherwise, who will bring that high quality, robust data in the country? And LMICs, when we talk, and now like the WHO, and fortunately, coincidentally, licensing for the LMICs and rare cancers group. So that's such a demand that we are missing out from this part of the world, and even more is Africa. You hardly have any studies. So but I think it becomes a responsibility for centers like us to be able to find out mechanisms towards generating robust, good quality data through these eye-opener workshops, and and then because it's much more needed. There is a lot of data from the West, but I think there's a lot of data which is they're looking up to from coming from Asia, and a big miss out from Africa. So I just thought I would put that point as well.
So I'll give you a story. When I was doing my fellowship at Censoring Hospital, I worked under Dr. Rob Bristol at I first heard the term of clinician science, surgeon science. I did not know about this.
Yeah.
And they had dedicated time. He's a clinician. He looks after penetrating cancer. Also has a lab. So he had a dedicated time for doing lab-based practice.
I agree.
So in the West is definitely there. I've seen them clinician science 30, 40, 40 to 50% of time dedicated for research and 50% of time. I think that this should also start happening in our setting.
It's very much needed, and not only the amount of time, but the amount of staff to the patient ratio. I mean, I am, when I say that how many are we, I see our medongs who are so understaffed. So I think the staffing, because again, it's not only the research, it will influence the practice. Still looking at anybody might be a great pathologist or an oncologist, but if your quality will be influenced if you are seeing that phenomenal number of cases. So I think that sensitivity has to be there, and I totally agree that there should be a dedicated time. But I think that with having said about the dedicated time, we need to also see the output also which is coming. So and I think you will agree that I do deal with heterogeneous tumors, sarcomas, and 200 types. So there are individuals who are able to bring out some, and so it again, not judging anybody's abilities, but I do value that dedicated time and being sensitive towards the staffing, the usual issues that we have.
Not much dedicated time because of the high burden of clinical services. Do you think incentivizing good quality research will be a boon?
Absolutely. So, like I said, I'll tell you, again, coming to the first, the empowering and, and again, not saying that somebody's not done research, has not done a good work, but at the same time, who have brought in a good amount of research in practice, which is influencing, which is bringing it more. I think we need to empower that, and that will create a system in which everybody feels more. But again, if we have not dedicated time and there is so much of work, your thought process with this, so many distractions, I don't want to judge people on WhatsApp and everything, your free thinking is also affected, and you can't bring those questions, which you can and you should in the clinics. So I think one needs to have a system of some free thinking to be able to bring good questions. Absolutely. Time, and then of course, empowering and showcasing those works and celebrating that work.
And also it's a situation where you take yourself off clinics, you don't have control on the standard of care. Okay, so somebody else is doing clinic, and then you are doing research. How will you make sure that the standard of care is employed? So that is why you need to have a dual role. Okay, now if you want to have dedicated time for research, another person is actually sitting and seeing your patients, which you are supposed to see. So you should also have dedicated, I would say you should also share your accolades with the other person who is actually sharing your time. It's a teamwork. So it is about building the team who will recognize you as a research contributor in the team, while the other person will be the clinician contributor. And you should not always be the face of that research. You should be sharing that with the other members of the team. So that's how the team will build. If you don't have dedicated time, you should have dedicated personnel. That's other way to actually help yourself build the research. So build your research team, which should not be only doctors. You should have other scientists and all. So that's how you build up your research. You should have other science people coming in and helping you with research while you continue with your clinics.
Basically, people in the team are not just workhorses. You just take them along with them when you just do your research, and incentivizing them by putting them as co-authors or even co-corresponding authors, giving them importance in that sense. So not only monetary incentivization, but also incentivizing them by putting them in as co-authors, which also help them to make to succeed also. So that's next one. It comes to next one, another 10-15 minutes. Is it okay? So, sorry. Is it okay for another 15 minutes?
I
Or
think
are you feeling hungry?
the statistics part.
Invite some questions from the audience. Oh yeah, if you want, you can ask.
Basically, I'm a medical person from a corporate sector. So, how do you think that corporate hospitals should be empaneled enough to do or compete with the research of the academic institutes? We are just doing a kind of a service right now at the, yeah, anybody. Understand the question, which always.
See, if you are at a corporate hospital, don't compare yourself with Tata or CMC. What can you do there? You can still do quality research coming out of a corporate hospital. So find a question that can be answered in your hospital. Okay, now you are saying I don't have funding. Okay, the hospital will not give funding. Look at from a funding agency point of view. Any of you, if you're going with a proposal, why should they fund you? Because they are not sure that you're going to finish the research, isn't it? That's what happens. Funding agency also has performance output evaluation. How many has been funded, how many papers came out, how many has been impactful. So they will also think at funding the research which is going to be fruitful. So what will they look at? They look at your career background. They will look at whether this fellow will finish it or not. And how do you strengthen that if you don't have any background? You have good collaborators. So find somebody who has a good research background to vouch for you. That's how you make your research strong. And then funding will come. With your first funding and first research, if you have completed, that's your background. The next one will be easier. So that's how you build it up. It's not, there is no one-step solution to a phase 3 triple blinded, what he was saying. So it will never happen as the first one. It will, you have to, what Vijay was saying yesterday, it has to happen, build upon small ones. And it can happen in smaller hospitals.
Next one coming to financial and operational balance. That's another big challenge. Financial, yes, Dr. Xavier had before going ahead that funding opportunities not, they have started coming up now. When in the West, I've seen that there are good funding opportunities. Are there any operational barriers for implementation of clinical trial? Like for example, in LMICs, we have huge data burden. Collecting that data burden is it's an important thing, but we really don't know much about it, how to collect it. Although now the solutions to it are coming up, having softwares where databases are coming up with like RedCap or like Castor EDC. I put them all. Some important ones have also coming up. Online forms like SurveyMonkey, Qualtrics, and Google Forms are also there. But in the West, do you have a very good system of data upkeep and data so that at a later stage you can retrieve that data and analyze it whenever you want?
Yeah, I mean, it's all nowadays, technology is there. And it's even in the West, people do not have the funding. If you're a junior faculty member and you're just starting doing research, you don't have the funding to be able to use the electronic data capture systems that are expensive. What we do have is that we have research institutes and research centers that have that. And then the investigators come to those and get affiliated with they get the infrastructure, they get the support and so forth. So for example, at the Population Health Research Institute where I am, we have the softwares, we have the electronic data capture systems. And so a junior faculty member at McMaster University School of Medicine has an idea. They come to us and say, this is an idea that I have for a study, maybe a retrospective study, maybe case control study, maybe a cohort study. And they postulate that to us. And our institute says, yeah, this seems like a reasonable thing. We will support you. And so we can provide that support. And now they get that infrastructure. So one of the things that one idea is that you establish units, organizations that like Tata that have that the infrastructure from as personnel as well as software and experience and knowledge to support the junior faculty. So the junior faculty says, I cannot, my person or my group of 2 or 3, where do I get? How do I get it? I have to learn myself. Even RedCap, I have to learn it. Where am I going to get my study coordinator? Where am I going to get this? I need to get funding for this. So now you have the burden of funding. You have the, so you need to see if research organizations, oh, I work in oncology, so why don't I go to Tata and talk to them and see, even though I don't work at Tata, can I get funding from them because my idea is a good one? And so now you have this other internal funding mechanism. You don't have to go external to ICMR to get funding, but maybe Tata will not fund the study. It's okay, yeah, we will fund the study if you can get external funding for all the work, but also get external funding to pay for our group here to manage your data, to help you with this and so forth. So this is one possibility to explore. Just a smaller, yeah.
Another important thing and as an operational barrier, as I see, is that there is for us, we sometimes find difficulty in patient recruitment, which we actually, when I was doing my fellowship at Censoring, patient recruitment was not a problem because community doctors were also aware of the various trials which were going on in the market. However, here is a big problem. Do you have any thoughts about it? So how do we have a solution to overcome this challenge?
Yeah. So over the years, I think from the time I have joined my residency, I have seen that, like you very rightly said, that patient recruitment is, and partly it is patient recruitment has been a problem, and partly and very correctly it is because of the fact that the ethics committee and data safety and monitoring units are now very particular about the consenting process, the informed narrative, whether it is documented and whether a copy was given and all. And those things make it very strict. And the second part that has become a particular problem now in an institute like Tata, there are multiple randomized trials going on, and you cannot have a person participate. Usually, you cannot have the same patient participating in 2 interventional randomized trials. So based on these 2 facts. The patient recruitment has been a problem. I think we were just discussing right now. I think we have to have a pragmatic solution. One of them is that India probably doesn't have that much culture of multicentric accrual. I think we have to start embarking on multicentric accrual projects. We cannot be now challenging ourselves saying that, oh, we are seeing 50,000 cancer patients a year and we can do a 900 patient oral cancer trial in 5 years. No, that's not going to happen now. And probably it's not very robust also in terms of what is the value of the data. I think we are all realizing that. So personally, I think that now when we are designing a trial, we should look at least target 5, 6, 7 centers where this trial can take place. We should speak to like-minded people before we start the trial and submit into our IC and see that they are on board, and then we go around the trial.
Good. It's a good idea. So rather than having unicentric trials, start having multicentric trials. Balu, another important thing I wanted to, and I want your thoughts about it. How important is culture of patient advocacy, and how important is the culture of advocacy to community to send patients higher institute for clinical trial, and how patients can be advocated to participate, especially in our culture, in our sector.
So I was just coming to that. So your solution is from a researcher perspective, how to get more patients. So from a patient perspective, why are they not participating in research? One is they don't understand what you say. 2 is they have a fear. Okay, so if they don't understand what you say, one is, as I said yesterday, step down your level of writing has to be in a very patient-friendly manner, and it has to be invitational. Secondly, the language barrier. So what we are building, we understand, because we have to speak 7 languages if I have to work in CMC. So the language barrier is a major thing. So what we are trying to build is to use AI solutions to actually query in 22 Indian languages. We are helping the patient, even a voiceover can ask questions about the research so that they can get. So these are things that will get established with time. Thirdly, how do you address their fear? To address their fear, that is where patient advocacy comes in. So you should have a patient advocacy group which will understand about your research, and you should tell the patient that please call up these people if you have any doubts, because they are going to talk to you from a patient's point of view. And it is now mandatory to have patient representatives in committees which will actually approve your research. So when this comes in, the patient recruitment and awareness would be better. I don't think that culture exists in India, evolves in India of referral. If I see a patient first, I'll treat and then send it to the next person. That's what happens in India. So I cannot answer that at this point.
I'll give an example. The GHSC, German Hospital Study Group, central office is in Cologne. Every community physician who sees a Hodgkin's lymphoma patient has to refer the patient to the central office for being randomized to any or for accrual in any of the trials. That's how they have actually developed their entire system. It might be very hierarchical, but that has actually worked for them. Each and every patient of Hodgkin's lymphoma is in some sort of a.
So answer to that is we have something coming up called the ABA, which has a unique patient ID. ABA number has to be generated, and CDAC is also developing a universal EMR for India. So the idea is that once you get registered, and it can be either SNOMED or ICD coded diagnosis, you would be able to get information of new incident, rare diseases, all those. So it will take some time to evolve in India. It will be faster, but as 5 years down the line, there will be some solutions for these.
So we are getting some messages, multi-center trial patient advocacy, maybe start having this particular thing
So for patient advocacy, one thing to maybe even consider is at the design stage of your study, involve patients in looking at the protocol, seeing if your outcomes are patient-centered, seeing, what are the potential adverse events and so forth. Are these tolerable, acceptable? It may be hard to recruit if you're now getting things that are going to be really bad for them. So involving them at the design stage may be useful.
It's a very good idea, but it's a small place. Patient levels in our country.
So there is one startup called Patients Engage. I came across them in Credo. They kind of take in your patients, train them, and create a patients advocacy group for you. So there are people like that, NGOs like that, who are actually helping you create that.
Last one, very controversial. As a researcher, I do my research, but my published research gets rejected. So here, if you see there, you think that there is publication bias, and some trials actually don't publish negative results. They are not very proactive in publishing negative results. You think that is correct? And what about open access and article publishing practice? And last but not least, there are certain predatory journals which publish for some sort of a fee, which we cannot afford. These are the challenges. Does everybody agree to this?
I mean, it's a very large problem that we are facing, but we are not addressing, where we have to get funding, we have to do the research, we have to make sure it gets published, we have to pay for publication, and we have to pay for view, while the journal just hosts it. And the reviewer also, we have to do the reviews, and no remuneration, nothing. So this model, I don't know how this is sustaining, because as a group, we are not collectively questioning, and we don't have an alternate model to offer also. So I think it's a very large problem, which as a scientific community, we are not addressing. But
I agree that it's not being well addressed. On a personal level, I tell you that if I get a request to review an article for an open access journal that charges an incredible amount of fee for somebody to publish, I refuse to review it. And when they ask you in the comment, why are you refusing? Because you're too busy or this and that. And I said, because as a policy, I do not review for journals that charge a lot to publication and pay nothing for a free review. That's what my line is to them. So on a personal basis, one tries to do it, but I agree, it is really a very bad challenge, poor system, at the moment?
So there are open repositories where you can actually publish your preprint research, unreviewed or unverified ones. If you are getting, and then that can generate a DOI number, which can be used for citations also.
Statement from you as well as Shweta.
I want to really come in here because I am apparently, wear hat of an editor. I have been an author, so I've seen it at different levels. Foremost, I would like to say that we need to resist this predatory journal effect and paying for that. If you are having, and I remember last year, Vinita shared a very beautiful journey of her work. Rejected, learning, getting over it. I don't know if and it was so stimulatory. You don't give up, you keep answering. Rejections, there's a lot of work, the inputs coming from I've learned a lot from the reviewers, including language, everything. So we need to be positive, open-minded towards when we get comments. And the reviewers are mostly blinded reviewers, so I don't think that there is mostly, but yes, there can be a bias for studies coming from this part of the world. But again, partly we are responsible because there are a lot of couple of fake news also which has emerged. So it creates some sort of bias, and journals do look, which region the studies are coming, and accordingly the reviewers have been also identified to be sent. So that is one thing that but as we evolve, bringing out better studies, better trials, I think we will also, and that's the responsibility as an investigator or an author, we should have it in mind that we are not only showcasing our work or sharing, but a responsibility of also, our country's reflection. So I'm positive on that aspect. But I really, inform the authors. In fact, I keep mentioning offhand also to resist this predatory journals, because if you fall a prey to it, it's a reflection of your work in the long way, because you are being also perceived that, oh, he or she's published in a predatory journal, so the quality of your entire work becomes questioned. It might be a good work, but you've fallen, it becomes questionable. So I think we need to be aware and not fall into that prey of the predator. And I think there was one important point also you said. I'm just trying to remember.
About publishing negative.
Yes, so I think it's, I don't know about the trials. I think y'all esteemed will know, but I think I very rightly echo that, a negative result in a well-designed study is saving a lot of people who are thinking to pursue. And it's a great, I think, opportunity to people who are thinking in that direction to stop, because these results have shown negative. So there's no bandwagon sort of research going into that direction. So it saves, I think it's a good, and I don't know, but journals have a perception towards not publishing negative results, which I won't. But I'm very serious about this predatory. And again, preprint. I think we've been asked about. We don't have a policy at this point. We're not encouraging, but I'm a bit also skeptical about the preprint. As an editor in chief of a journal, so I would like to know everybody's thoughts. Of course, it's a good opportunity for the investigator to show his timely research coming out, and it has a DOI number. But again, from an editor's perspective, if, we're still, I think, in our learning phase towards perceiving the preprint as a publication, which is seen and goes to a journal. So I'm just in that learning mode to know about this.
Just one more thing from Shweta, then you can take.
Regarding the predatory journal thing, I think absolutely. I think all have at some point probably been near to falling prey to it. What I can suggest is there are lists available online about predatory journals and predatory publishers. Whenever, if there is even a small bit of doubt that journal can be predatory, usually what red flags me is that whenever a journal is writing a mail of, oh, please come and publish, and we are publishing, and we were happy to see this article, and we think that your expertise is very good for this. I actually double check it unless it's the journal is very well known to me. It doesn't happen at my stage of career. Yeah, so please go through those lists of publishers and journals. And the second thing was regarding the preprints. I think, yes, recently, as Dr. Balu mentioned, preprints are being available, but I have had very unfortunate experiences with preprints. I think some of the really bad works are also getting shown in preprints because they are not peer reviewed, and they mention it also that they are not peer reviewed, and people are actually been citing it also. And some of these things, when they come out actually in full thing, it is completely different from the preprint because the preprint was not peer reviewed.
I mean, that's the caveat it has. I mean, you tell that it's a preprint, it's non-peer reviewed, but your work is out there so that somebody knows that, okay, this data exists. Rather than watching it 3 years later published in a journal in a much more curated fashion, you already have your data out. So if you feel that the time is lost in waiting for a journal to reply, this is where you can actually put your raw results out so that collaborators will come to you. You can actually modify on this.
I'm getting the signal that we should stop. Thank you very much, all the panelists, for your heartfelt comments here. I wanted that to come out. It has come out very well. I hope you enjoyed it. I can have one-to-one sessions about all. So thank you very much.
Thank you very much, Jayan. Thank you very much, panelists. That was a marathon discussion, but you still managed to, hold the attention of the audience, which itself, speaks a lot about the quality of discussion. So I have, we are going to break very briefly for lunch before we get back for the protocol development session. It is going to be on sample size calculation mostly. So the statisticians will get into the act now. But I think, I must definitely allow Dr. Bangalore to have at least half an hour, to have a leisurely lunch and then, get back perhaps. But, one more thing that is happening here is we have set up a booth on the fourth floor in the Sapphire Hall because we want feedback from all of you. Not all of you necessarily, but at least, some of you. So if you can be so kind enough to go and, talk to the camera there, we'll be able to record your thoughts about the workshop, and you can be really open about, whatever you felt, or whatever you, yeah. So it will only help us to improve further. That's all. Okay.